Hello everyone, welcome to my YouTube channel. So we are back with another deep dive video, and this one will talk about the large language models. And we will start with very basics, like we will start with what is RNN, and then we will slowly go into the RLHF part for LLM. So this would be a long video. So at least like this video content is around 3 hours. So if you are planning to watch it, maybe you can break it down into smaller sittings and then watch it, grasp it, and like digest the content, then again come back to the later parts. So all the portions of this video will be divided into sub chapters so that you can easily consume the content of this video, and slowly you can get to the end of this video. But if you're looking for something very short in this space of large language models, so this video is not for you. So this is a very in-depth video, so where we will start with very basics of RNN until we will go to very different concepts of large language models, the attention mechanism, and how the attention mechanism is now being used for uh, LLMs like Llama 3 or Mistral models. And we will also look into those concepts. And in the end, we will talk about the RLHF part for the LLM, right? So let's go through each of these topics at first. Then we will do a deep dive on this each part of this video. So first one, we will start with the RNN, where we will look into the mathematical details and the equations of RNN, how it is different from traditional traditional multi-layer perceptron networks. And then we will also talk about what are the demerits of RNN. And then slowly we will move into the LSTM, how LSTM can solve the issues that are present with RNN. Then we will also talk about machine translation task using sequence to sequence model, which is kind of a encoder-decoder architecture, which we will talk in detail in this section of this whole video. And slowly we will introduce the attention concept with bidirectional RNN, and we will see like how you can introduce RNN with attention using an encoder-decoder architecture. Right. So then we will move to the more recent developments in the attention network, which are like self-attention, masked multi-head attentions, then sliding window attentions. Those we will slowly get into those and see how those are working with some type of visualization, right? Then we will talk about the positional encoding. Mainly, we will talk about rotary positional encoding because that is kind of being used models like in Mistral or Mixtral. So then we will talk about what is group query attention. So this from this part 6 onwards, these are like the recent developments that happened in the field of attention mechanism and how the much faster operations that we are able to do using this concepts like rotary positional encoding, group query attention. Then we will talk about KV cache, and slowly we will move into the rolling buffer cache. And then we will talk about what is prefill and chunking, which is also used in models like Mistral. And then we will talk about this mixture of experts, which was got very famous with the introduction of the Mixtral model. So then slowly we will talk about the different phases of LLM. So there are separate phases that are being uh, done in case of the LLM, so that we will talk about three different phases of training LLM. And in the end, we will talk about how RLHF comes into the training process of LLM and how that can be used to solve and align the LLM to the human preferences, right? So this would be a long video, as I mentioned, like this would be a 3 hours content. So I will ask you to break it down into smaller settings, go through each of the contents, digest the content, then move to the next section, right? So I hope you will like this one. Let's get started with this, with the content of each of this 14 or 13 parts in this video.
Episode, I wanted to talk about the sequential neural network, which is nothing but RNN or LSTM. How what are the problem associated with RNN and how we can tackle using LSTM. So that we will talk about in next few videos. So yeah, without further delay, let's get started with sequence modeling, right? So if I take the example of sequence modeling, so some of the data which are sequential in nature is like stock price, right? So if I pick up a particular stock, then that stock's current price, which is nothing but ST, will depend on the stock price of ST minus 1 or ST minus 2 or whatever previous day's stock price, right? So we will see like this ST, which is nothing but a current day's stock price, has a correlation with the previous values, right? So this is where the sequential data or the sequential modeling comes into the picture, when there is a high correlation of current timestamp value with the previous timestamp values, right? So this is one of the example of sequential data. Another example is natural language text, right? So if I just write down one of the example, like Virat Kohli is a great player, right? Is a great player. Now this has a certain meaning, right? Now if I write down this sentence in a different way, like is Virat Kohli is Virat Kohli a great player, right? Is Virat Kohli a great player? Now this, if you see, the sequence of word defines the meanings, right? Previously I am saying that Virat Kohli is a great player, but I have just changed the sequence of the words, like is Virat Kohli a great player, right? That is kind of a question which is coming into the second sentence, right? But if you just use any particular neural network, NLP architecture, which is like count vectorizer or TF-IDF, which just calculates the frequency of the words. So both of these two sentences will have the same frequency, right? Because the words which I have used has occurred in the same manner in both these two sentences, right? So you're using a technique like count vectorizer or a TF-IDF will not tell you the exact difference between these two sentences, right? So in those cases, we want to use a recurrent neural network where we have a certain memory, right? So memory, and also it can tackle different timestamp datas, right? So now you might have a question at this point of time, that why we should use a new kind of neural network, why we cannot use the multi-layer perceptron which we have already introduced in this course, right? So few of the issues which are present with multi-layer perceptron is like it is not suitable for sequence data, which is the sequence data is nothing but like t, it has data like t plus 1 or t minus 1, so it is not suitable for that, right? And it's also not suitable for variable length input, right? So here if we try to visualize the normal neural network using this, like where we have first layer, which is like nothing but the features we are passing through the network, like f1, f2, f3 and f4, and then we have a hidden layer where we have stacked multiple nodes on top of each other. We have two hidden layers, one is this, another is this, then we have the output layer, right? So we are kind of if we are thinking that this is a binary classification, so we have only one node, right? But it might happen, the example which I was taking, right, the sentence can have variable length, right? But this is kind of a fixed length input we can only give to a multi-layer perceptron. That's why the multi-layer perceptron will not work in case of sequential data. And also here this output, if I denote this as output, will only depend on the current input values, right, which are nothing but f1, f2, f3 and f4, right? It will not have any link to previous data or previous row data, right? So but if we design the network in such a way that it has a memory and it also has your current output has a function of previous timestamp values, then it will be able to capture these nuances which we are talking about, right? So your multi-layer perceptron will not work because of this three reason. reason, which is like it is not suitable for sequential data. It is also not suitable for variable length input, and also it does not have any memory, right? Now, how we can convert this multi-layer perceptron to come up with a memory, right? Now, let's talk about that. Now, if I just visualize this example, right? So, the same neural network, if I write it in this way, like instead of writing all the nodes of this hidden layers, I have incorporated into a box, right? And this is my input which is going on inside this box, and we are getting an output, right? This we can do, right? I hope you all agree. Now, if we just change the direction of this, if I just rotate this, right? Now, if I write it in this way, this is my input, well, this is my output, right? Still, we can do it using a normal neural network or a multi-layer perceptron, right? Now, if I just introduce a time component to it, right? So, if I have like 3 such windows, which are like, this is my xt, this is my xt plus 1, and this is my xt minus 1, right? And we have the corresponding output, which are like yt minus 1, yt, and this is yt plus 1, right? So this is also we can do at this point, right? Now this will still not suffice to our requirement, like we need memory, right? Your current timestamp output should be correlated with the previous timestamp value, right? Now what we can do is we can create a connection between this, right? So this is like the connections we are creating, and this connection we generally call, in case of recurrent neural network, as hidden state, right? This is your ht minus 1, this is ht, and this is ht plus 1, right? So if I just look this closely, so my yt, which is this timestamp value, will have which is nothing but a function of xt, which is obvious, but it also taking an input of ht minus 1, right? So which is a previous timestamp output, right? So now we kind of introduced a memory to the network, and it can take it can have a correlation or a function of the previous timestamp values also, because ht is nothing but also is a function of xt minus 1, right? So in that way we can convert a multi-layer perceptron to a recurrent neural network just by stacking the nodes on top of each other, then rotating. So this is where I have stacked multiple nodes, and this is where I have done the rotating, and after that I have introduced collections between each of the steps to bring a memory component to this multi-layer perceptron, right? So I hope you are getting this concept, like how we can convert a multi-layer perceptron to a RNN, and we can introduce the concept of timestamp along with memory, right? Now this can have multiple timestamps also, right? This is like we can have several other timestamps, and this will not be limited to the fixed length input, right? It can have a variable length input also, right? So this is the concept of RNN. So here we are kind of just drawing the same architecture which I have already explained to you. We have our input, which is nothing but xt, we are getting output of yt, and ht is the hidden state we are also getting, and that we are kind of using as a input for the next timestamp, right? Now we can unfold this and we can write it in this way. So we have the same network going on for each timestamp, right? So this is like for each of the timestamp we have kind of unfolded it or unrolled it, and we are getting a output for each of the timestamp. So it's the same network, this is the same network which we are using, and we are kind of unrolling it for the time periods, right? It's not that we are creating a new network every time a new input comes, right? So we are using the same architecture, and we are kind of passing the data sequentially to this same network, through this same network, right? Now what we can also do is we can also stack multiple RNN layers on top of each other. So if you see, my xt is the input, then we have layer 1, where we are getting an output of HT1, and then we have also another RNN layer which is HT2, and we are finally getting the output which is YT, right? Now if we just unfold this is how it will look like, right? So this is where we can stack multiple RNN on top of each other and do complex operations to maybe getting a better result using this architecture, right? Now, if I just look into the mathematics of each of these operations, right? So we have our xt, which is nothing but the input. Then we have this node, which gives you the ht, and we have the output, which is yt, right? Now, if I introduce weights in each of this path, right, from my input to hidden layer, if I name it as whx, which is nothing but the weight which is collecting the hidden layer to the input, right? And then we also have WHH, right? So HH is nothing but hidden to hidden, right? So that we also have a corresponding weight to that, and finally we have a weight associated with the output, which is nothing but WYH, which is collecting the hidden state to the output layer, right? Now we can write down my HT in this way. So this is activation function. Then we have my xt, which is multiplied by whx. Then my hidden state is multiplied by whh, and we are also adding a bias, right? Now my ht with this function, with this way of writing, is now a function of current timestamp input and also the previous hidden state, right? And once we have the ht, then we will again use activation function, and we will pass we will multiply the ht with the wyh, and we will add a bias to get the final output, which is nothing but yt, right? So I hope you are getting an understanding of the mathematics that is going on. So we started with the input, then we kind of multiply that input to a certain weight, and the previous timestamp hidden state we also multiplied with WHH, and then we kind of added a bias, and we are getting HT, and using that HT we will also get the YT, right? Now there can be different types of RNN network or different types of RNN architecture. One can be a simple one-to-one, which is this. Then we can have a one-to-many architecture. Like if I just take an example like image captioning, right? So we are passing an image as an input, which is nothing but X, and it's kind of generating a caption for that image, right? So if I just passing an image of Virat Kohli playing cricket, so it will generate a caption of like Virat Kohli is playing cricket, right? So it's kind of a one-to-many architecture. Then we have many-to-one, right? So many-to-one is like we are passing a sentence. So this is my sentence which we are passing, and finally at the last timestamp we are getting a sentiment, right? So this is another type of RNN architecture where we kind of doing a many-to-one, using a many-to-one architecture, and we are doing a sentiment classification, right? Then we have different tasks like machine translation. There we generally use many-to-many architecture. So this is like a simple many-to-many architecture, and then we can also have a many-to-many architecture where we have a encoder-decoder architecture, right? So this part of the network is what we call as encoder. This part of the network what we call as decoder, right? So in the encoder side, we pass a sentence, say like in English, and it can convert to a sentence which is like Hindi, right? So decoder will kind of decode that English sentence to a new language, which is Hindi, right? So this is the different types of RNN which you also can visualize and which you can think of. I just wanted to take you through, like one-to-many, many-to-one, then many-to-many. All these are like different types of RNN architecture, right? So then there is another type of RNN architecture, what we call as bidirectional RNN, right? So far we are seeing that your current timestamp output, which is nothing but YT, is a function of current input, which is xt, and the previous timestamp hidden state, right? But we can also incorporate the context from the backward direction also, right? Okay, so in case of bidirectional RNN, where we have like the forward and backward context, now your YT will be a function of your xt, and also it has the context from forward and also from the backward direction, right? So with that, it has certain it has certain benefits, like it can use the context from the past context and also the future context, so it will kind of give you better results when we are generally working with like text which has context coming from previous words and also from the future words, right? So your while making any prediction, it has two distinct states which are like ht forward and ht backward, right? Now the advantages of using bidirectional RNN is like it will increase the accuracy of your model, and then also it will have the context from past and future, right? So your prediction will get more context to give better results, right? But it also comes with certain disadvantages, which are like as we are kind of calculating the context from backward and forward direction, and it will have the additional computational complexity, right? And it will also take longer training time, because it needs to calculate the hidden states from the backward and forward directions, right? So these are the things which I wanted to let you know. Like using bidirectional RNN, you can give forward and backward context to the model, and which can generate better outputs. Right now, let's talk about the backpropagation through time, which is very specific concept to RNN, and also the vanishing gradient problem, which are related to RNN. Right, so if I have this different timestamps, right, starting from x1 to xk, and we kind of unrolled our RNN, and where each of the timestamps we are generating like y1, y2, and also the corresponding hidden states like h1, h2 till yk, and that is the last timestamp output, right? And we have the corresponding weights associated like WXH and WHH, right? And we are kind of incorporating both those weights, and we are calling the final weight as W, right? Now, given the input sequence, right? So my input sequence is nothing but x1 till xk. So our ht is nothing but a function of current timestamp input and also the previous hidden state, right? So with that, what we will do is at first we will calculate the loss or the error at each timestamps, right? So here we will have for this timestamp, which is the timestamp 1, we will have a error which is E1, then we will have error 2, error 3, till at the last timestamp we will have the error associated with EK, right? Okay, now the backpropagation through time, right? What we generally do in case of backpropagation through time is once we get the prediction vector, which is nothing but yk, we calculate the error, the ek. Now ek, now to optimize the weights, which are nothing but w is again a composition of whh and wxh. We need to take the derivative of y error with respect to w, right? So this is what we generally also do in case of multilayer perceptron. But the catch here is we are kind of need to take this derivative with respect to time, right? We are kind of passing each timestamp and then calculating the error. So we need to accumulate those error and then calculate the derivative. So your del E by del W will be a function of summation of t equals to 1 to t, and it will be a derivative of del Et by del W. Right, once we have that del E by del W, then we can optimize the weights using a radial descent steps, right? Step, it will be a function of like this, del ek by dw will be calculated in this way, right? So where we start using the chain rule, we will start with del ek by del yk, which is nothing but the output at k timestamp. Then we will go back in the time and we will start with del yk, and we will access the hidden state along for that particular output. And using the hidden state, we will roll through the time, and we can like write down the other timestamps, and finally we will get this del h2 by del h1, and then using the del h1 we can like write it del h1 by del w, right? So this is kind of, we are going back through the time to access each of the timestamps error, then we are calculating the derivatives, right? So this we can write it in this way, where we kind of the time associated things we can write as a product, which will start from t equals to 2 to k, and we can write del ht by del ht minus 1, right? This t will run from 2 to k. So this we can write it in a more compact way. Now if I just write my ht, so this we are already aware that ht is nothing but activation function, then multiplied by whh multiplied by ht minus 1, then wxh multiplied by xt, right? Now if I take the derivative of this, right, so by taking the derivative of this, we will get the output as this, like, which is the derivative of the activation function del whh multiplied by ht minus 1 plus wxh multiplied by xt, right? And we will multiply this with whh, right? So whh is coming from this partial derivative, right? Okay, so once we have this, we can plug this equation 2 into the equation 1, right? So once we plug in this, we will get this formulation, right? Your dw del ek by dw will look like this, right? And this term, which is this term, right? So this term will cause either a vanishing gradient problem or exploding gradient problems when we have a larger sequence. So that's why we say that when we have a larger sequence in RNN, we will have a vanishing gradient problem or exploding gradient problem, because this is a multiplicative term, right? Which we can see is this is nothing but a multiplicative term. And in case of multiplicative term, if we when the derivatives are very small, right? So this, if we multiply two small numbers, then you will get a smaller number, right? So if I multiplied 002 with 0.001, we will get 0004 times 0 del 2, right? Which is much smaller than each of these two numbers, right? So that's why as this is a multiplicative term associated with this derivative of RNN, in case our derivatives are very small, after multiplication it will become much more smaller, right? So which can cause your derivative to be very small, and your learning will not be proper using this, right? And also we are this also can cause vanishing gradient problem when k is large and derivative of tan h is smaller than 1, right? So that will, once we take the derivative of activation function, which is nothing but tan h, so your tan h derivative will be also smaller than 1. Now if I multiply again the smaller derivatives with a value which is lesser than 1, it will also reduce that value, right? So which will cause the problem of vanishing gradient, right? So it can also have the problem of exploding gradient when your WHH are large enough to overpower the smaller tan h derivative, right? So in both the cases, we can have either vanishing gradient problem or your exploding gradient problem. So in case of vanishing gradient problem, your del ek by del w will become very close to 0, right? So this is the thing which will become very close to 0. And if I plug this value, which is very close to 0, then your w will be, after the updation of gradient descent, your w will be not be changing very much, and it will remain stagnant, right? So your learning will not be proper, and your gradients will not help in optimizing the weights associated to this network, right? So I hope with this understanding that your derivative formulation, if I just do the math and calculate the derivative of del ek by del w, we can see that they're associated multiplicative term which can cause the vanishing gradient problem. Because if the derivatives are small, and also we are taking the derivative of tan h, which can be also lesser than 1, and accumulating all this, your whole derivative will be very small, your learning will not be very much accurate, right? So that's why we say that your RNN has a problem of vanishing gradient. So I hope you got an understanding why I am saying that your RNL has a problem of vanishing gradient. And with that, this is one of the very frequently asked interview question, like why RLL has a vanishing gradient problem, right? So I will share this notebook also with you all, so that you can do this hands-on mathematics operation and see how this is resulting in a vanishing gradient problem. Okay, so the last thing which I wanted to talk about is, in case of sequential data, we have a newer dimension to our data point, which is t, which is nothing but the number of timestamps in the sequence, right? So in case of general data, we have L cross D dimensions, but in case of sequential data, we have like L cross T cross D, right? And if I just give you an example, this is where the data will look like if you want to work with RLL or sequential model. Here we have 5 cross 5 cross 2. 5 is like we have 5 rows here, or the L equals to 5. Then we have 5, which is nothing but the number of timestamps, right? So here we can see like this is 1, 2, 3, 4, 5. So we have 5 timestamps data, and we have 2 features associated with that, right? This is first feature and this is second feature. So your t equals to 5 and your d equals to 2, right? So this is how you can visualize this using this box, which is nothing but L cross T cross D. And you always need to remember that when we are passing our data to a PyTorch model, your data has to be in the form of L cross T cross D.
All right, so in the last few videos, we were talking about the RNN, how the RNN architecture looks like, the different equations that are involved in the RNN architecture, and how also I described how if we take the derivative of the error with respect to the weights, how RNN suffers a problem of vanishing gradient, right? So the derivative with respect to the weights we generally call as back propagation through time, because we are kind of calculating the gradients at each time stamp, and then we are doing a back propagation, right? So with that, let's try to understand how LSTM works and what is the architecture of LSTM and how it can solve the vanishing gradient problem which we have seen in case of RNN. Okay, so now let's get started. So first of all, like if I just look into the architecture of LSTM, it has certain inputs which are like xt and ht minus 1. It also has a new thing which got introduced in LSTM, that is a cell state, and also it outputs ht, right, which is nothing but the hidden state. So the new thing which got introduced in case of LSTM is the cell state. So actually this cell state is kind of responsible for tackling the vanishing gradient problem, which is associated with the long-term dependencies in case of RNN, right? Now there are also certain gates which are new to LSTM, and all these gates generally update or control the cell state, right? So the gates are like forget gate, input gate, and output gate. So these 3 gates are mainly responsible for updating or controlling the values of your cell state, right? Now let's first talk about the forget gate. So the forget gate generally works the given the new information. The forget gate controls what information in the cell state to forget, right? So if I just write down the equation, this is the equation where we have a sigmoid activation function. So this is nothing but a sigmoid activation function, then the weights associated with the forget gate, and we have the 2 inputs which are like ht minus 1 and the current input which is xt. So these are like my inputs,
and this is the weights, and after taking the sigmoid activation function we get the forget state output, right, which is nothing but ft. So as it uses a sigmoid activation function, so it will the output will always be in the range of 0 to 1. So whenever the value is closer to 0 or 0, that means let nothing through, right? So it will like forget the things which are there in the cell state, right? And whenever the output is 1, that means let everything go through of cell state, right? So if I just take an example, right? So uh, if this is my the output of ft, right? So if my output of ft is like this, 0 0 0 1 1 1 0 0, then again 0 1, something like this. And if you can see, we are doing a element wise multiplication with cell state here, right? So if my cell state, which is nothing but this, it will also have a similar shape, because we are doing a element wise multiplication, so this ft and ct has to be of the same shape, right? So we have certain values like 2.5, then 001, and all this, like another few values. So whenever we multiply these two things, right, so whenever it is 0, whenever the places where the forget gate value is 0, so that values will be eliminated, right? So this will become 0, this will also become 0, because the first three element itself is 0, right? So you can understand, like whatever the value that is coming from the previous cell state, which is nothing but ct minus 1. So this actually it was ct minus 1. So once we multiply this ft and we do element wise multiplication with fct minus 1, so certain parts of my previous cell state will be forgotten, and whenever there is the forget gate value is equals to 1, so that will be remembered and used in the further process of my LSTM, right? So I hope you got an understanding with this, like what is the job of forget gate. Now let's come to what is input get, right? So in case of input get, what we are doing is, in the input gate decides what information will be added to the ct, right? So in case of forget get, we were kind of eliminating few of the informations from the previous cell state, but using the input get, we will decide what new information will be added back to the ct, right? So if you just look at the math or the equations, it has actually two sections. So this is the weights associated with this part, and also we have a weights which is like wc and wi. So with the help of wc, we take tan h activation function, and we get this ct dash. So this part will be ct dash, which is nothing but this equation, which is tan h activation function, then weight multiplied with the inputs, which is ht minus 1 and xt, right? And we also get this it. So it is nothing but the sigmoid activation function, and we are multiplying weights with the inputs, which are like ht minus 1 and xt, right? And after that we are kind of doing a element wise multiplication, right? So this output will be my input gets output, which is nothing but uh, C tilde element wise multiplicated with it, right? So that will be the output of the input gate. And again, if you see here, we are using the sigmoid activation function here, and then we are doing element wise multiplication, right? So whenever we are using a sigmoid activation function, the output will be always in the range of 0 to 1. And after that, if we are doing a element wise multiplication with any other input, so some parts will be zeroed out and some part will be kept as it is. So zeroed out when the sigmoid activation function's output is equals to 0, and will be kept as it is when the sigmoid activation function's values are equals to 1, right? So once that is done, then we will add back this information to the ft, right? So this path is nothing but ft multiplied element wise multiplicated with ct minus 1. So after that we will get the updated ct value, right? So this is after doing this addition. So if you see, we will update ct minus 1 to the new candidate or new candidate cell state value, which is ct. So ft will be multiplied with element wise multiplication with CT minus 1, which is the operations during the forget gate, and this is the input which is coming from the input gate, right? And we finally get the updated value of CT, right? So with this we are kind of forgetting few parts of my previous cell state using the forget gate, and we are adding few things using the input gate, right? And we get the new updated cell state value, which is CT, right? So after that, the last gate which is there is output gate, right? So the output gate decide what information encoded in the cell state will be propagated as HT. HT is nothing but the input for the next timestamp, right? So if you see, like at first it calculates the output gate output, which is OT. So the OT will be calculated using this sigmoid activation function. So your WO is the weights associated with output gate. So WO will be multiplied with the inputs, which are like HT minus 1 and XT, and then we use a sigmoid activation function, and that will be element wise multiplicated with the tan H of CT, right? So here again we see that this OT is nothing but will be the output in the range of 0 to 1, right? So it will decide what information from the CT, right? So CT is we are using a tan H activation function on top of CT, and then we are multiplying with the OT, right? So OT is the sigmoid activation function we have used. So this output gate will decide what values will be propagated as HT, right? So HT will act as an input to the next step. So this OT, which I have written here, so that will be if it is like we are using a sigmoid activation function, so some of the values will be 0 and some of the values will be 1, right? So in that way this OT will look like, and whenever it is 1, so those informations from CT will be forward propagated as HT, and whenever it is 0, so those information will be removed from the CT while calculating the HT, right? So I hope you got an understand that the output gate decides what information that is already available in the CT. So here this updated CT is coming here, and that will be multiplied with the tan H, and this is where we are getting the OT. So this will be element wise multiplicated, and we will get the final HT. So HT is nothing but your OT element wise multiplicated with tan H of CT, right? So the output gate will control what portion of cell state value will be given as an output as HT, right? So with this we will now talk about how the backpropagation through time in LSTM works and how it can solve the vanishing gradient problem, which we have seen in case of RNN, right? So the output in LSTM incorporates the cell state, right? So that we have seen. So using the cell state value, we are calculating the HT, right? So once HT is calculated, we can compute gradients over T timestamps, and which we also did in case of RNN also, right? Now if I just consider the gradient of the error terms for some timestamp K, right? So it can be written as DEK by DW, and that can be written as this, which is same as which we did in case of RNN also, right? So it has a product term which is DCT divided by DCT minus 1, right? Now if you remember, CT is nothing but this. Now if I take the derivative of with respect to del CT by with respect to del CT minus 1, then we can use the multiplicative rule, which is like this. If I just take, so it will look like U multiplied by dv by dx plus v du by dx, right? So this is the formula which we will use. So this is the derivative formula of the product term, and that we will use, and we will get this term, right? So and we can see each of the term here is like in the summation form, right? And if we denote each of these terms with like a t, b t, c t, and dt, we can see this is the equation 2 which we are getting, and all these terms are additive in nature, right? Now we can put back 2 into the equation 1, and we can get the final equation for del ek by dw, right? So you can see, like in case of RNN, this term was a multiplicative term, right? But in case of LSTM, this is a additive term, right? Now how LSTM can solve the vanishing gradient problem? Because this term is additive in nature, so if all these values are very small, right? So if we sum that, it will not vanish in case of what we were seeing in case of RNN. If we multiply small values, the values will become much more smaller. But in case of addition, it's not the case, so it will not have the problem of vanishing gradient. And also there is a presence of CT, which is the cell state, in the derivative term, right? So here we can see that we have a term of CT. Here also we can see a derivative term of CT. So all that is present in the derivative of LSTM, right? So that CT will decide which part of the long-term dependency it should forget and which part of the long-term dependency it should remember, right? Using the different gates. So with that, it can pick up the crucial information from the long-term dependency, and it can keep the things which are required or which are essential, and throw out which are not essential, right? So with these two things, we can say that LSTM will work much better in case of long-term dependencies while compared with the RNN. The main reason is here the derivative term is additive in nature, but in case of RNN, the derivative term is multiplicative in nature, which has a very high chance of going into the vanishing gradient problem, right? And also the presence of CT, which will essentially remember the crucial part of the long-term dependencies and throw away the part which are not required, right? So yeah, so this is the one which I wanted to talk about in this video. So I hope you got an understanding of why how the LSTM works with different gates, and how the derivative of LSTM is much more simpler while comparing with the RNN, and how. So in the last few videos of this series, we generally talked about like RNN and LSTM, and how like RNN suffers from vanishing gradient problem, and also like how we also talked about how LSTM can solve that vanishing gradient problem, right? Now let's talk about a use case which generally is machine translation. So in case of machine translation, we generally use sequence to sequence modeling. So what is this sequence to sequence modeling is, right? So we pass some set of sequences, and also the model kind of outputs a set of sequences, right? So if you remember this diagram, right, so which we discussed in our previous sessions, that we have different types of recurrent neural network. So one of them is like this many to many one, right? So this is a many to many one. So if I just take this example, this is one of the example of many to many, and this is also one example of many to many, right? So in case of machine translation, we use generally this architecture of many to many, where we pass through certain sequences to the model, and then it outputs the different types of sequences in the decoder side. So this part of the model we generally call as encoder. So this is nothing but encoder, and this is where we get the output of the model, which is the decoder side, right? So in case of encoder-decoder architecture, in the encoder side, for this specific example, when we are talking about machine translation, so that this can be a simple language, any language like L1, which we are passing to the model in the encoder side, and the decoder side we will expect the model to translate that language to a different language, which can be L2, right? So some examples, like if you are passing your inputs like Bengali to this model, and it will kind of translate that to English, right? So here if you see, we are not taking the output of So we are not considering the output of each of this time sequence or the RNN. So this basically each of these are nothing but RNN, right? So here also we get certain outputs, right, at every time step. So we are not bothered about that. So we will not use that. Instead, we will use the hidden states, and that hidden states we will propagate to the next timestamps of the unrolled version of RNN, right? Now let's talk in detail how this sequence to sequence modeling is actually works. So as I was mentioning, in case of machine translation, so if our input language is say Bengali, then we kind of pass a sentence to this encoder side. So this part is nothing but encoder, and this is my decoder side, right? So this is the decoder side of my model. Here I'm passing a sentence which is, if you understand Bengali, then what I am saying is Ami bhalo achi. So that means I am good, right? So I am passing each of these tokens. So at first I will split the sentence to individual word, and then that word will be passed through a embedding layer, and that embedding we will pass through the model. So Ami is converted to an embedding which we are denoting as x0. So we will pass this x0 to this encoder side first timestamp. So that is like x0 we are passing to the RNN, and with some initial values of h0. So that we generally initialize with zero values, and we pass through this first timestamp, and that produces the output which is h1, right? It also produces the output here also, but we don't consider that. So that the hidden state we will pass it to the next timestamp, and the next timestamp I pass my next embedding representation of the second word, right, which is bhalo. So that will be converted to embedding of x1, and that x1 will be passed to the as the unrolled version of the RNN, and we will get the second hidden state, and in the end we will pass the word achi, right, and that will be passed to the as a third unrolled version of this RNN, and then we get a third hidden state, right, which is nothing but h3. So this h3 we generally call it as a context vector, right? So this is my context vector, which is the output of my encoder side, right? So that encoder side output or the context vector is kind of a representation of this whole sentence, right? So this whole sentence, we imagine that is kind of encoded in this hidden vector or the context vector, right? And using that context vector, we will pass the context vector to the decoder side, and in the starting point, while training the model, we will pass as a start of the sentence token to the first timestamp of my unrolled RNN, and that will kind of produce the first word of my English language. So if I'm doing a Bengali to English translation, so that will produce I, right? So actually this RNN produces kind of logit values. So that logit value we pass through a softmax function, and that softmax function will convert the logit values to probabilities, and that again will depend on the size of the vocabulary. So we will build a vocabulary. So when we will code this in the PyTorch, this concept will be much more clear to you, but for the timing, you understand that RNN produces the output. That output passes through a softmax layer, and that softmax layer kind of with the help of the softmax output, we pick up the most probable word, and that word we like if the model is well trained, that will produce I, right? So generally we pass this I as to the next timestamp as an input, and it produces the next output, which is y2, right? And that is equals to am, right? And then it goes on till it produces the last sentence, or it produces a end of sentence token. So this is not the end. There will be another step of RNN where we will pass the input as good, and that good will produce end of sentence token. So at that point of time, you kind of think that your model has produced the full conversion of one language to a different language, and you will kind of stop the iterations at the decoder side. So this is tell you, like, the first is we have an encoder and also we have a decoder. So in the encoder side we pass the one of the language, and in the decoder side we get a translated version of that sentence as an output. and in between we get a context vector. So that context vector is generally a representation of your input sentence of a particular language, and using that context vector we kind of try to generate the translated sentence. So this attention mechanism is related to the bidirectional RNN. So we will use the bidirectional RNN, then we will see how the attention mechanism works, right? So let's go back to the problem which we were trying to solve in the last video, like machine translation using sequence to sequence model. So here, like, we have certain inputs, and with those inputs we kind of create at first we get the, at the encoder side we get the hidden state, the H1, then using that we get H2, and then we will get the corresponding states H3, and we assume that the last state was H4. So all these intermediate states, the hidden states like H1, H2, H3, they are not being used fully. So we just hope that H4 is also kind of have the informations which are related to H1, H2 and H3, and using that H4 we kind of create our context vector. So we get the context vector here. So this is, I will mention as CV. CV is nothing but context vector. So this H4 will act as a context vector, and that context vector we pass as an input to the decoder, and decoder will start producing the output like Y1, then with the help of that Y2, similarly the other things in the end like YN, whatever the sequence steps we have, right? So with this we can understand that we expect a lot from this context vector, right? So we kind of expect that this context vector is kind of a representation of this full sentence, right? Which can be a problematic when we are having a very large sentence, right? So instead of focusing only the last hidden state, if we can we focus the intermediate hidden states also, right? And if we can generate the C4 or the CV, which is nothing but the context vector, with the help of all this H1, H2, H3 and H4, then we can like give lot of emphasis on the other hidden states also. And it might happen that for generating a particular step, your output vector, your output is only dependent on H2, right? So we can put more attention to this instead of putting attentions or the emphasis on the other hidden vectors, right? So that is the idea when we when we will talk about attention mechanism. So here if I again take this example, like we have H1, H2, H3 and we have H4, right? Now we have a context vector, so I am just mentioning this as C. So this context vector will not only depend on H4, so H4 it will always depend, but it will also depend on the other hidden states of my previously generated hidden state in the unroll version of RNN, right? So with that we will generate the context vector, and using this context vector we will start generating the first token and the corresponding other tokens, like this is like Y1, Y2 and Y3 and Y4. And also you need to be mindful that this context vector, for each of the output step, this context vector value will change. It's not that we have a fixed context vector. So for Y1 we will have a corresponding context vector like C1, this is like C2. Similarly we will have the other context vector for other outputs, right? And this will determine that which part of the input will we will kind of put more emphasis or more attention while generating the output, right? So I hope you got an overview of what is this attention mechanism, that instead of only using the last hidden state, we will also use the intermediate hidden states, and with that we will create a context vector, and that context vector will be different for each of the time steps output, right? So this is sequence to sequence with attention, right? And the other one which we discussed, which we also implemented in the last time, that was without the attention mechanism, right? Now let's go and check the detailed math of this, right? So I have this image where we have the same representation of encoder and decoder, but it's in a different manner. So if I just zoom out this, so if you see, there are few parts here. So this part which is coming up here, so that is my encoder. So I will explain each of these parts very much in detail, and this part generally represents the attention mechanism, right? And this is my decoder, right? So this is coming from the paper which was written by Bahadanu. I'm not sure like if I'm pronouncing the name correctly, but this is the one of the starting attention mechanism which came into the field, and with that, like a few later on, like few improvisation of this attention mechanism was done, and nowadays like attention is everywhere, right? So with this, let's get started. So in the encoder side, what we have is we have a bidirectional RNN, right? So this is like my forward directional RNN, and this is my backward direction RNN, right? So we have the context from both the direction, forward and backward, and each of this has a initial hidden states, which is like this one and also this one. So I will just zoom it up here. So if you just look it closely, we have two set of RNN. So these are like my forward, and this set of RNNs are going backward direction, right? And we pass our input here. So we kind of have individual words. Then we have a embedding layer. So this is nothing but embedding layer. So we pass our input tokens to the embedding layer, and we get an embedding representation, and each time step we pass it through the forward directional RNN and also the backward direction RNN, and we kind of get individual RNN outputs. Like for this time step we get output like H0 forward, H0F, right? And also here we kind of get H0B, which is like a backward representation, right? So with that, what we will do next is, so for every other time steps also we will get the corresponding two outputs from forward and backward directional RNN, and once we get that, what the general tendency is to concatenate those two outputs and we get a final hidden state, right? So this H0 is nothing but a representation of H0F, which is coming from the forward direction RNN, and H0B, right, which is the representation of hidden state related to the backward direction RNN, and we kind of concatenate and we get the H0. So with that we can also get like H1, H2 and H3, right? So this is all about the encoder part. So encoder part is quite simple. Here we, instead of using the unidirectional RNN, we are using a bidirectional RNN, and we are getting the outputs from both the directions, and we are kind of concatenating and getting the each of the hidden states, right? H0, H1, H2 and H3. Right, now let's talk about the attention mechanism, how the attention is generally working. So here we have the attention layer, where we have like initially we get A0, A01, A02 and A03, right? So now let's look into this, how this A0s are calculated, and also like the individual, like this E's and the capital E's, right? So we have three components which are being generated, and in the end we are getting the C1, right? We start with the H, then we get the corresponding E's, the small E's, then we get the capital E's, and in the end we get the C, right? So this is how the flow looks like, but let's look into in much more detail how the each of these mathematical steps are going on. So as I was mentioning, we have our individual H, which are like H0, H1, H2 and H3, and that we are passing to this A00, right? A00, A01, A02 and A03. So this A00 are nothing but a single layer feed forward neural network, right? So what are the inputs that are going inside this? We are having our regular H, which is coming from the encoder layer, the H0, and also we are getting the previous timestamp input for the decoder side, right? So if you see here, we have a S0, so that S0 is getting a flow here, and that is used as a input for this A00. So with the help of previous timestamp hidden state from the decoder layer and also the encoder layer hidden state, which is 80, we get like E00, right? So this is nothing but a single layer feed forward neural network, right? So with the input of this two, we get a different representation, which is E00, right? So I hope these things are clear. Like we get E00, similarly we will get E01. While calculating the E01, we will use the H1 as the one of the input. So S0 will be as it is, right? And then we get like E02 and E03, and this all these inputs which are like E0s, we pass it through a we pass it through a softmax layer. The softmax layer will kind of normalize these values, and which would be kind of the output will be like the sum of the outputs will be 1, right? So this is how this works. So this is I am showing the calculations for E00. So we take the exponent of E00 and then we sum the exponent of each of these terms, right? And we divide this E00 exponent of E00 with the sum of this all these terms, right? So which will be like a normalized value. So all this sum would be equals to 1, right? So this one, now we kind of get the capital E's. So we started with H, then we got small e, and we get the capital E, right? So with the help of capital E's, we calculate the context vector, right? Now how this context vector is calculated, you need to look here, right? So we have our H zeros which are coming from this encoder side, and also we calculated E01, E02, E03, and um, E04, right? So with that, then we kind of multiply each of these corresponding terms, right? H0 will be multiplied by E01, E02 will be multiplied by H1. So all this will be multiplied, and we will take the sum out of this. So when we get the sum, we get the C1, right? So with the this is the context vector related to the first time step, right? So now your C1 is kind of a context vector for this decoder timestamp, right? So similarly, we can generate C2, C3, and C4, right? So this C1, if I just talk about this context vector, right? C1 has access to each of these hidden states, right? H0, H01, H2, and H3, right? Now with this context vector, it can know like which part of this hidden state it should give more emphasis or more attention, right? So that is the basic concept. Like while creating this C1, C2, C3, and C4, your individual hidden states which are coming from encoder side will have a say, right? And with that, it will kind of uh, understand which part of the sentence it should give more attention or emphasis, right? So I hope you got an understanding of this context vector generation, and with that context vector, we will your encoder side will generate the corresponding outputs like y1, then we will generate like y2 and y3, similarly the last step output which is like yn, right? So this is how the basic math works in case of this attention for bidirectional RNN.
Alright, so in this video I want to talk about self-attention. So along with self-attention we will talk about what is multi-head attention and also masked multi-head attention. So these three concepts are quite essential if you want to understand what is sliding window attention. So to understand the sliding window attention, which I will talk about in the next video, let's first talk about what is self-attention. Right. So in case of self-attention, right, so we generally have this encoder-decoder architecture when we are like doing a machine translation task. So when we are like passing one language to the encoder side, so this can be a language called Bengali, and that we are passing to the encoder side. Each of this one by one we are passing each of the tokens of a particular sentence, and then we are like kind of calculating the hidden states like h1, h2, h3, and h4. Then h4 once we generate that will kind of act as a context vector, and that we will pass to the decoder to generate the further tokens in a different language. So that language can be English, right? So if you are new to this concept of encoder-decoder and how this sequence-to-sequence model works, I have a few of the details videos from my Deep Learning with PyTorch playlist. So I will also mention the link of those videos in the description of this video, so you can go ahead and get your concepts cleared with those videos, right? So the problem with this sequence to sequence model is we are expecting a lot from this context vector, right? So we are expecting this context vector to like incorporate all the hidden states which are here, right? And with that hidden states incorporated in the context vector, then we are translating it to a different language. That can create a lot of problem, but what I have talked about in my Deep Learning with PyTorch playlist, so you can go ahead and look into those videos. Now to tackle this, what we can do is we can make this a few changes in this architecture. So what we can do is, instead of only depending on the H4, we will also incorporate the other states, or we will also make available all the other states from this encoder side for the context vector, right? So, and along with that, we will also calculate attention score. So if for an example, like if y2, when we are translating a particular language to another language, and for a particular token like for y2, if that has more emphasis on a hidden state which is associated with h3, right? So the attention score will be higher for this h3 for y2, right? So each of these individual states, each of these individual tokens will get a context vector like c1, c2, c3 and c4, right? So all this will get an individual context vector, and then with that it can like using the attention score, it can like put more emphasis on certain parts of the input sequence, and with that the translation will happen in a much better way, right? So this is what a basic concept of self attention is in case of encoder decoder architecture, right? Now let's try to visualize this this basic form. So what we generally have is we have this xi, which is my current input, and for that we are kind of calculating the dot products between xi to the all other input tokens, which are like x1, x2, x3 and xt. Then once we calculate the dot product, so this dot product is kind of gives you the what is the similarity between these two tokens, and once we have those dot products, then we can normalize using a softmax, and after that we can calculate more context aware embedding vector for xi, right? So this is like using this j equals to 1 summation to t multiplied by aij. With xj we can calculate the ai, so that is kind of a more context aware embedding vector for the xi, right? So this is a very basic form of self attention, where we are kind of, first of all we are doing a dot product, then normalizing using a softmax, and then we are calculating the final embedding vector, which is more context aware, right? So here you can see there is no learnable parameters in this approach, right? So what we can do is we can now bring in certain learnable parameters through which while doing the back propagation in this neural network, it will also learn those parameters during the back propagation. So we have three trainable matrices which are like wq, wk and wv, right? So this three trainable matrices are multiplied with the input sequence to get the query key and value, right? So we get the query vector, or the query vector by multiplying wq with xi, then we have the key vector and also the value vector, right? So what we are doing is we are passing the x, and x is getting multiplied with wq, wk and wv, and we are getting the corresponding qkv, right? So this query key and value, this concept came from the attention is all you need paper, and that is kind of the learnable parameter which we have introduced in this architecture, right? So once we have this matrices, what we do is we do this operation, right? So at first we'll multiply q with k transpose. Then to minimize the variation of this, the variance of this multiplication of q multiplied by k transpose, if we don't like divide this with the root of the dimension of k, then we will get a huge variance of this multiplication, right? So just to minimize the variance of this multiplication, we are like dividing this qk transpose by the square root of the dimension of k, right? Here, just for an illustrative purpose, I am taking an example like this is my input sequence, which is like attention is all you need. So the length of this sequence is 5, right? Then we have this k, which is the embedding size, right? So embedding size is like for each token, right? So if I talk about this attention, it will be represented with a long stretched out vector, and this shape of this is k, which is usually in attention all you need paper is 512, right? So with that, what we will do is, let me first clear this. Okay, so what we will do is we introduce the q matrix, which is n cross k, and then we multiply with like k transpose, which like after doing the transpose the shape is k cross n. Now we are multiplying n cross k with k cross n. So and then we are dividing by the square root of k, right? Just as I mentioned, this is to reduce the variance of this dot product, right? Then what we are doing is we are doing a softmax on top of this whole operation, and we are getting an output. This output is nothing but a attention based matrix, and that the shape of that is n cross n, right? So this is what we call as attention based matrix, where each part of the token is kind of have a attention score associated with a different the other tokens that are present in the input sequence. N is nothing but the sequence length, right? So if I just take this example, so we have this n cross k, which is our q. So this is like 5 cross 512, right? So as I mentioned, like inattention is all you need in paper, this k is equals to 512. So for this example, the shape of q is 5 cross 512. Then we are multiplying with, like after doing the transpose, we are multiplying with a shape of 5 cross 12 cross 5, and then we are like dividing it by the square root of k, and then we are taking the softmax, and what we are getting is in the output is 5 cross 5 attention based matrix, right? So n is nothing but the sequence length which we are mentioning here for this example. So after that, what we are doing is we have done the first part, like doing the softmax operation on this. After doing the dot product, then we need to multiply this with the value vector, right? So we got the attention matrix, which is like this n cross n matrix, and that we will multiply with v. So v is nothing but a shape of n cross k. So we are multiplying n cross n with n cross k. So the output what we will get is n cross k, right? So this what we call as embedding vector, and this embedding vector is much more context aware. So we are calling this as attention based embedding, right? About what is multi-head attention, right? So we talked about self attention, and now let's talk about what is multi-head attention, right? So in the multi-head attention, the concept remains the same, just that we are having multiple heads which we will calculate using the formula that we have already talked about using the attention mechanism, right? So we have our input. That input is get multiplied with the different learnable matrices which are like wq, wk and wv, and we get the corresponding query key and value vectors. So once we have that, what we will do is we will divide each of these matrices, like the q will be divided into 3 matrices like q1, q2 and q3, right? So we are kind of introducing this multi-head by dividing the q to multiple heads, right? So similarly we will do that operation for the k matrix and also for the v matrix. So we have corresponding k1, k2, k3 and also the v1, v2 and v3 for q1, q2 and q3. Now we do this attention operation. Using this formula, we will calculate each of these heads, which are like h1, h2 and h3. using this same formula which I already talked about in the last few minutes. And after that, what we will do is we will concatenate each of these heads like H1, H2 and H3, and that gets multiplied with a output matrix which is WO, and we get the multi-head attention, right? So in one head it may be picking up certain characteristics of the input sequence, and using multiple heads we assume that it will pick up the other qualities of the input sequence, and it will be more diverse in terms of calculating the attention of the for different characteristics of the input sequence, right? So once we have this multi-head attention, then let's talk about the masked multi-head attention, right? So why we need first of all the masking, right? So in case of encoder side, right, so this is the encoder side example. Your any of the tokens, right, if I talk about this all token, right, so that token can look into the past tokens, the previous tokens, and also it can look into the future tokens, right? So this is what it can happen in case of encoder side, because encoder side we are mainly generating the embeddings, and embeddings can look at the past behavior of the input sentence or the input sequence, and also it can look ahead for the future tokens or the future words for the particular input sequence or input sentence, right? But it is not the case if when we are talking about the decoder side, right? So this is what we have talked about the encoder side. In decoder side, it is mainly the decoder is trained for next token prediction or the next word prediction, right? So we need to mask out the future tokens for each of these sentences, each of these tokens, right? So for attention token, it can only look at till this part, and after that it is all zero, right? So because it cannot look ahead what are the tokens that are coming in the future. If it looks into the future tokens, that is kind of cheating, right? So just to avoid that, we will mask out these tokens, and we will make all the future tokens for a particular token as zero. So for like is token, it can like this values will be masked out to zero, and similarly for other tokens the future values or the future tokens are masked out to zero, right? So all this value which I am showing here, you can see like the diagonal elements are kind of highlighted because that is kind of a word is looking into itself, and those are using a self attention mechanism, those attention score will be much more higher. But these values are random, so I have like used random values in this matrix. So don't think like why the values are not adding up to 1, because after doing the softmax each of these row wise elements will be summed across summed equal to 1, right? What we do in case of self attention for this decoder side is, or the causal masking we also call it, we will make these future tokens as minus infinity, right? So once we make these future tokens as minus infinity and then apply the softmax, these values will become 0, right? So this is the concept of like masked multi-head attention. Let's get started with what is sliding window attention, right? So as I mentioned in the last video, I talked about self-attention mechanism. So what we do in case of self-attention mechanism is we multiply Q with K transpose. Then to minimize the variance of this dot product, we divide it by the square root of K, which is nothing but the embedding size. And once that is done, we will get a attention matrix, right? So in multi-head attention we generally do in case of the decoder side, right? And in the decoder side, the main task of the decoder is to produce the next best token or the word next. So to avoid the cheating, what we will do is we will mask the future tokens with negative infinity, right? And once we apply the softmax, this negative infinities will become 0, right? But in case of sliding window attention, what we are doing is we are picking up a size of a window. So here for this example we are mentioning the size is equals to 3, right? So it will, every token will have a window size of 3, right? So for this, if I just take about the last example for this need token, right? So it will have only the sliding window size of 3, and all the other tokens, so this is like the first token for this word, this is second, and this is third, right? And all the other tokens which are available in this particular for this particular token, that will be marks to minus infinity, and once we apply the softmax, this will become as 0, right? So similarly for this token, right, u, right? So here also, like, we are applying a sliding window attention, so only it will have access to this first, second and third token. So the other token which is present here, that will be marks to minus infinity, and that will become 0 once we apply the softmax, right? Now, why we need to apply a sliding window attention, right? So in case of sliding window attention, what we are doing is we are focusing on the local context, which is like the recent past, rather than the context which is like far back, which can be irrelevant for the current token also, right? And this will also can reduce the number of dot products that we need to do, right? So once we get the attention matrix, then we multiply with the value vector, right? And then we get the context aware embedding. So if we are masking out these things to 0, then the dot product will be reduced significantly for the future operations, right? So that is one of the benefit, like the operations can be much more faster when doing this matrix multiplication operation, as we are reducing the dot products significantly by applying a window on this context of each of these input tokens. Then the question comes is, will this degrade the performance, right? So with a proper example, I will try to show this will not have an impact on the performance. The performance will remain as it is, but we will gain the performance in case of like inference time, and also the irrelevant context will be like thrown away, and only the relevant context will be used for doing the attention mechanism, right? And this is the basic concept of sliding window attention. Now let's talk about how it looks like and why we are saying that it will not have an impact on the performance, right? So this is actually this image is from the Mistral paper. So we can see in case of vanilla attention, all the elements that are above the diagonal element is maxed out to 0, right? For the decoder, so Mistral is kind of a decoder based model. So the basic operation or the basic job it has to do is to predict the next base token, right? So that's why the future tokens are marked to 0. But in case of sliding window attention, the future tokens are also marked to 0, but after a certain window, those values are also zeroed out. So you can see like these values are also zeroed out here, right? So that is the concept what we have in case of sliding window attention. The values which are above the diagonal, that is also 0, and also this based on this sliding window, like here we are considering 3 as sliding window, so all these values are only considering 3. Here we do not have any further past context, so we are considering 2 only, and for this token it is only like the first token that will be considered during the further dot products in this while calculating the attention mechanism. So what this paper talks about is the effective context length is very much same in case of the vanilla attention. Now why it is saying that? So if I just take the example of this token, right? So it is looking into only this few tokens, right? But in turn, this token is looking into the other this tokens, right? And again, this token is kind of looking into the all other tokens that are present here. So this is the concept which you can relate to convolutional neural network, right? So once we like pass through a filter or a kernel, it may look into the for a single window, but once we stack multiple layers of CNN, so you can think that it also looking into the full context of the image, right? So as we mentioned, if you remember the architecture which I have drawn, so this attention part or this window is kind of stacked on top of each other, which is like nx times, right? So using multiple layers, we can say that using the sliding window attention, it will not lose the context, and it will have actually the full context for a particular token, right? So it can look at all the past future tokens that are present if we are stacking multiple layers of sliding window attention. right? So this is actually the benefit of using sliding window attention. We are gaining in terms of inference speed, but we are also not reducing the model performance by stacking multiple layers of this sliding window attention, right? Now let's talk about the example which we have and see how this sliding window attention does not have any impact on the model performance. So if I just take this example, like which I have been talking through, the attention is all you need. So we have this 5 cross 5 matrix where the diagonal the elements that are present above the diagonal are masked out to 0, and also the contexts that are beyond the sliding window of 3, that is also masked to 0, right? So once we do that, so if I just visualize the context length for each of this token, so attention token can have only this as the context length, right? So ease can look into only attention pass token, right? All is kind of looking into this two tokens, and u is looking into this two tokens, is and all, right? So this is nothing but what we have here in this matrix itself. So if I just talk about u, which is present here, it can look at the only this pass two tokens along with its own token, right? And similarly for the last token, which is need, it is looking into the u and also the all token. So you might think that, yeah, now we are getting a performance issue because the last token, which is need, is only looking at the past two tokens. But this is what we are doing at the layer 1. Now if we stack multiple layers of sliding window attention, what we are doing is we are taking this as input. So if I just take the pin, so this will become the input for this matrix, and we are kind of creating a similar 5 cross 5 matrix with this architecture, right? And also we are masking out the tokens which are kind of beyond the sliding window size of 3, right? So your first token is attention, then the second token is attention is, so this is actually the second token, this is your third token, so this is your attention is all, then we have the is all u, this is actually the second last token, and this is actually the third last token, right? So which is represented here, right? And all the values which are beyond the size of window equals to 3, those are marked to 0. So what we can see here, right? And after that, if I just again calculate, like for each token, what is the context it is looking at the past. So for the last token, if I just take the example of need, so need is actually looking into, so this is need, right? So let me clear this screen and again take the pin. So this need, so this is the last token, right? So this is which is actually the token which is associated with need, right? Which is actually this token, right? So this token is actually being represented here, and this is actually looking into these two tokens, right? So this two token is, if you look at this, if you take the unique tokens out of this, this is actually attention is all u. So this is actually looking into the past 4 tokens, right? So if you just take the unique tokens for this last two window, it is actually looking at the full context of your inputs sequence, right? So that's why we are kind of saying that if we stack multiple layers of sliding window, it will not lose out any information, but we can significantly reduce the dot products, and which can in turn give a boost in the inference time, and also it will keep the output of the performance metrics as same as it is in case of vanilla attention, right? So first of all, let's go through why we need positional encoding in case of transformers, right? So this is the basic architecture of transformer, which is kind of stood the test of time, but one of the few changes that are brought into this architecture is replacing the positional encoding with rotary positional encoding, which happened in case of the models like Llama 2 and the Mistral series of models, right? So before going into the rotary positional encoding, let's talk about what is positional encoding and why we need at first this thing, right? So for an example, like if we take these two sentences, right? Ram is behind Arun and Arun is behind Ram, right? So these two sentences, if we pass through the transformer architecture without positional encoding, this two sentence will remain same, right? What we do is we have this word RAM, and what we convert this word to embeddings, and then we add a positional encoding, which is can be absolute positional encoding, and then we get the input, right? So by adding the embeddings with the positional encoding, we get the input, and then we pass it through the encoding layer and subsequently to the decoder layer, right? Let's talk about what is this positional encoding or the absolute positional encoding is, and we are talking about the sinusoidal functions which we are using in case of the this attention all you need paper, right? So we have a sentence which is SN, which is kind of a series of tokens which starts from I to N, and those we are represented as WI, right? So once we have those tokens, then we pass it through embedding layer and we get a series of embeddings for each of these words which we are denoting as XI, right? Which will also start from 1 to N. So this is like we are converting like the tokens to the embeddings. So once we got the embeddings, what we do is we calculate these three matrices like query, key and value, which we also talked about in the last few videos in this Mistral spelled out series. So actually this encodings goes through a function which is like for every query key value there are specific functions like fq, fk and fv, right, where we kind of pass the embeddings and also the position of that vector or that token. So then this fq are this all this f are nothing but a function which is like which multiplies the weights associated with like wq, wk or wv, that we multiply with this embedding plus pi, right? So this xi is added to the pi, which is nothing but the positional encoding, then we multiply with the corresponding weight vectors to get the output which are for every query key and value pairs, right? And then this pi, right, which we touched upon here, is pi is nothing but a sinusoidal function which comes in the form of this, right, and also this. So this I is nothing but the position which we are talking about, the position in the sentence or the input, and this t is the position of the embeddings. So if we have converted to embeddings, right, now for our example, like one token is represented with a stretched out 512 embedding size, right? So this is like 0th position and this is like 511 position. So this t is nothing but the position in the embedding, right? So for this is like for this t equals to 0, and this is for the last one, this is t equals to 511. So I hope these are the few of the benefits which we get when we are using a sinusoidal function, is that they are continuous in nature and it can scale to any input sequence length easily, right? So this is also because of the continuous nature of the sinusoidal functions, right? So this is one of the type of positional encoding which also comes directly from the Prefill, which is attention is all you need. Then we have another type of positional encoding, what we call as relative positional encoding, right? So this relative positional encoding is kind of captures the distance between two pairs of tokens. So if the tokens are like two distance apart, then there would be a specific bias term which is like bij that will be added to the token. As we are kind of calculating the relative distance between two tokens, and the distance between two tokens is generally calculated using this query and key value matrices and during the attention calculation process. So what we do is we add this bias term to the multiplication of query and key vectors, and we do not touch it for the value vector, right? And this we generally do it for every pair of tokens, right? So if the two tokens are like 3 distance apart, so that time every time specific bias which is same will be added to this the multiplication of this attention mechanism, right? And this, as I mentioned, this is only used for query and key and not used for V, right? And this we generally use in case of the T5 model.
But there are certain issues with this relative positional encoding. So one of the issues is like if you just plot it by the input length and with respect to the inference speed, you will see that this T5 model are kind of slower for longer sequences, right? This is because of the we are putting in an extra step of like this calculating this trainable bias in the attention mechanism, right? So once we do the multiplication of query and key, then we need to add this trainable bias to the attention mechanism, so the inference speed becomes slower in case of this T5 relative positional encoding, right? Now let's talk about what we are trying to explain in this video, that is rotary positional encoding. So before that, let's talk about what is a rotation matrix. So if we have this vector v0 and we want to rotate this vector v0 to v dash, right? So now we need to rotate this vector by a angle of theta, right? R theta is nothing but a rotation matrix, which is like cos theta minus sin theta. Then we have the sin theta and cos theta, right? So this is the rotation matrix which we multiply with v0, and then we will get a new vector which is rotated by an angle of theta in this two-dimensional space, right? Okay, now first of all, like if is your first token in the input sequence, then that is represented by this vector and this vector. And if now the if ease becomes your second token in the input sequence, right? So the first token is like attention and the second token is ease. So ease will be rotated by a vector by an angle theta, and we will get this new representation of ease, which is this, right? Now if ease becomes the mth position in the input sequence, right? Now this ease will be rotated by an angle of m theta, right? So this is what the representation of rotary positional encoding, which is more or less similar to the absolute positional encoding. Now if we have two tokens, right, which is all and u, right, which are like theta distance apart, right? Then if that all u kind of got shifted and now it is kind of the third and fourth token, so that the pair of this two vectors will be rotated and shifted, but the relative distance between these two vectors will be maintained, which is theta, right? So that's why we kind of say that rotary positional encoding is kind of a mixture of absolute positional encoding and also the relative positional encoding, right? So the first thing which I talked about here, so which rotates a vector by m theta, is kind of a representation of absolute positional encoding. And this example which I talked about here, where the relative distance between the two vectors are preserved, that comes from the concept of relative positional encoding, right? So we combining these two things, we kind of get the rotary positional encoding. So as I mentioned, like vectors are rotated by m theta, which is the absolute position of the token in the sentence, and the relative distance between the vectors are also maintained. The angle between the vectors are same, and the dot product between these two vectors will always remain same between two set of vectors, right? So this is the concept of rotary positional embedding. Now let's see how we implement this in terms of mathematics, right? So we have this function which is fqk, and here this is the rotation matrix which rotates a vector by m theta, and then we have this x is a vector that we are trying to rotate. In this example, this is kind of a two-dimensional representation of x, and so we at first apply the linear transformation to the query and key vector before applying the rotation, right? So at first this query and key will be multiplied with x or the input, then the rotation matrix will be applied to rotate the vector and get the rotary positional embeddings, right? So this is what we talked about was for two-dimensional vector. Now we can like scale this to a multi-dimensional vectors also, right? So these two embeddings, it will rotate by this m theta 1, right? And for this two, it will again rotate for this, and for this through it will rotate this. So this is how we can like scale the rotary positional encoding in case of multidimensional vector or multi-dimensional. So I hope you got an understanding of what is this rotary positional encoding and why we need it, and what is how it is a combination of absolute positional encoding and the relative positional encoding. So with this, all right, let's talk about grouped query attention in this video. Right. So before understanding the grouped query attention, let's talk about let's do a recap of what is multi-head attention. Right. So if you remember this diagram, we have the input, then the input goes through few of the matrix multiplication with like WQ, WK and WV, and we get the corresponding QKV matrices. So in case of multi-head attention, what we do is we kind of split each of these matrices into different heads. Like Q will be splitted in three heads like Q1, Q2, Q3. Just for the illustrative purposes, we are showing that we are just splitting the Q with three heads. So this number can vary according to the size of the head that we are using in this attention mechanism, right? So similarly, we will also divide the K matrices into K1, K2, K3, and also the V1, V2, V3. We will split the matrix of V matrix into V1, V2 and V3, right? So for each of these heads we kind of do this operations which are like given this using this formula softmax of QK transpose then divided by the DK, and then we will multiply with the each of the V heads with this, right? And once we do that, we kind of get individual heads which are like H1, H2 and H3, and after that we kind of concatenate each of these heads, and then we multiply with our output matrix which is WO, and we get the multi-head attention, right? So this is kind of a recap of what is a multi-head attention is. Now let's talk about what are the different issues that are present with this multi-head attention. So in case you have watched my video which is related to KV cache, so there are I have talked about like there are certain repetitive tasks that we are doing in case of generating the new tokens using this attention mechanism. So that those repetitive tasks you can take care by using a KV cache, and by that you can like eliminate the computational bottleneck using the KV cache. Now there are other challenges with GPUs, right? So modern GPUs are kind of quite fast in case of computational tasks, but when we are accessing the different matrices and we are kind of transferring one matrix to one GPU to another GPU, that kind of is much more slower if you are compared with the task, right? So computational tasks like matrix multiplication, those are very fast in case of the modern GPU, but transfer of matrices from one GPU to another GPU or retrieving the matrices is bit slower while compared to the computational task, right? So in case of multi-head attention, what we generally do is we need to repeatedly load and transfer this large query key and value matrices, which can result in memory bandwidth bottleneck, right? So that's actually we are trying to solve using this grouped query attention. And so generally we use two techniques to solve this. One of them is like multi-query attention, and the one which is the focus of this video is the grouped multi-query attention. Now let's talk about what multi-query attention is and what are the demerits of that multi-query attention and how we can tackle that using a grouped query attention, right? So in case of multi-query attention, what we do is we kind of split only the queue in multiple heads. So for this example, we are using heads equals to 8, so just for illustrative purpose. So this is like we are kind of splitting the queue into different heads which starts from Q1 to Q8, and after that what we will do is we will keep the K and V matrices as it is, and we will name them as K1 and V1. And then what we do is we kind of do the operations which are related to calculating the attention matrix, right? So we kind of multiply like Q1 with K1 transpose and we get one head. Then we also get another head by multiplying K2 with K1 transpose. So we will multiply each of these components of query matrices to this K matrix, and we will get 8 heads. right? So after that, what we will do is we kind of do this other operation which are related to like taking the softmax and then multiplying with the V matrix, and again we will get different heads which are related to after multiplying with the value matrix. And after that, what we will get is 8 different heads which starts from H1 to H8, and then what we will do is we will kind of concatenate those heads, and then we multiply with the output matrix and we get the multi-query attention, right? So this is the basic concept of what multi-query attention is. We have we have divided the queue into different heads, but keeping the K and V matrices intact, and we will have only one head for K and V, right? So this will kind of reduce the transfer of memory and the loading different matrices which are related to K and V, and we can tackle the memory bandwidth bottleneck using this technique, right, with the help of multi-query attention. Now there are a few different demerits of this multi-query attention is, so one of the demerit is that if you just check the blue score using this multi-head attention and multi-query attention, so this is actually the multi-head attention where the blue score is 26.7, but as we are kind of reducing the heads which are related to K and V, right, so the K and V equals to 1 here, so that will kind of reduce a degradation in the performance. So just also that degradation is slight in nature, so we can see like it is 26.5 here, right? So but it is quite obvious that using a lesser number of heads which are related to K and V, that will kind of cause a degradation in the performance of the performance in the output of if we are doing a English to German translation task, right? But in case of inference time, you will see like there is a significant improvement in the inference phase. So you can see like in the encoder side, the speed is like 1.7, and then that is 46, right, for the decoder phase in case of doing the inference. But in case of multi-query attention, we can see like it is 1.5 and this is 3.8. So previously it was like 46, and using this concept we have reduced it to 3.8. And also in case of beam force search, you can see like at the decoder the speed was like 203, and now using the multi-query attention we have reduced it to 32, right? So these are kind of significant reductions in the inference time, and which can result in much faster inference. And these numbers which I have talked about, those are in microseconds per output token, right? So this is kind of a significant improvement which you can see using this multi-query attention. Now let's talk about what is grouped query attention, grouped multi-query attention is, right? So we have the input, then we get the QKV matrices, and we kind of split the queue into different 8 heads. So in this example also our head equals to 8. So we kind of split the Q matrices to Q1 to Q8. Now instead of having only one key and one V, what we are doing is we are kind of using 4 key matrices and 4 V matrices. So starting from K1 to K4, and we are kind of grouping the query heads into each of these K matrices, right? So K1 is kind of grouped to Q1 and Q2, K2 is grouped to Q3 and Q4. Similarly, the other query matrices are grouped to different K matrices, right? And then we kind of multiply with V1, V2, V3 and V4, and in the end we get like 8 different heads which we again concatenate and then like get the grouped multi-query attention, right? So this is actually the basic concept of grouped multi-query attention. Instead of having K equals to K and V equals to 1, we are kind of grouping the query matrices to different K matrices and different value matrices. And query attention is kind of a mixture of your multi-head attention and the multi-query attention, right? So here your H is kind of same instead of query K and V, but in case of multi-query attention, this is K and this is your V, so that is equals to 1. But here we are kind of grouping different query matrices to one K matrices, and then we have the corresponding V matrices, right? So this is values of K and V matrices. Then your group query attention becomes multi-head attention, right? But when your group equals to 1, then your group query attention will become the multi-query attention, right? And now let's talk about the inference time, and let's compare with this group query attention inference speed with the inference and also the performance along with the other multi-head attention and multi-query attention. So if you're just seeing a grouped query attention with like a considerable number of groups, then your performance is also good, and also the inference time is very low also, right? So this is kind of where it lies. And similarly, we kind of get like multi-query attention. XSL is the size of this the heads of K and V matrices. So we can see the performance is kind of low, but inference is again like quite similar to what we have is in the grouped query attention, right? So I hope you got an understanding of what this is. So in case of grouped query attention, we are kind of gaining in case of performance along with the inference time, but which is not the case if you are using the multi-query attention. So in case of transformer models, right, we have like once the model is trained, we have this model where this is kind of the model which we have trained. So let's try to visualize like the inference phase. So this is after once the model is trained. So once the model is trained, we get this model, and during inference phase, right, inference phase, what we try to do is we try to do the next word prediction, right? So for the example like which we have been using in this series, the input token or the input sentence, right? So attention is all you need. So this is the input sequence which we are trying to feed to the model, and it will kind of generate the output what we are looking for. So how it happens in the next word prediction is, at first we feed kind of start of sentence token. So this is kind of start of sentence token that will be feed here to the model, and we will expect that the model will produce the output as attention, right? So then we will kind of add this to the input. So attention will be added here, and this will be fed to the model, and the model will kind of now produce ease as the next token, right? So ease will be again added back to the input prompt or the input context, and now we will expect the model to produce all, right? So once all is also produced, that will be added back to the input, and that will kind of increase the context length and also the context, which is easier for the model to understand what would be the next token. And with the help of this much context, it will produce u, right? So similarly this process will go on, and then we will feed u, which will produce need. So once the need is added to the input sequence, then the model will produce end of sentence token, right? So generally this is the kind of the process what goes on during the inference phase and the next word token prediction. And all you can see, like we have lot of repetition of task, right? At the last step we wanted to produce this need, right? So we want to have this need as kind of the output, and once we feed this need, we also need to feed this all of the previously generated tokens, right? So all these tokens we are also feeding to the model, which will kind of enhance the context for the model, and it will it will give the more details about what is the previous context of the model. But this also has additional complexity, right? So this is like the additional complexity which model has, which is kind of also a repetitive task, right? So this is kind of repetitive. So can we like remove this repeating part, right? Can we cache all this part which we have already done, right? So this token generation is already done, right? So we don't need to feed this again and again and do the computation, all the query key value multiplication, at first the query and key value multiplication, then the v value multiplication, and in between also we need to like divide it by the dimension of the d, and also we need to take the softmax, right? So there are a lot of steps which goes on in this whole process, and a lot of things we can cache, right? So that's why the concept comes as KV cache, like where we will try to reduce the computation, and we will reduce the repetitive task that we have been doing with this architecture of the vanilla transformer architecture in the Attention All You Need paper, right? Let's go ahead and try to visualize how the matrix multiplication operation happens in case of Attention All You Need paper, right? So this is the formula which we have, the attention formula, where we kind of multiply the query with the k transpose, and we pass the corresponding tokens. So the first token related to query and key value is passed, and we do this matrix multiplication, and we get the output which is q t transpose, right? And that is kind of a one vector that we kind of produce. So if I just talk about the dimensions, so this is, if I take the model dimension as 4096, the embedding dimension, so this is also 1 cross, so once we do the transpose, so this will become 4096 cross 1, right? So once we multiply this, we will get a 1 cross 1 vector. So I hope you got this concept, like how this multiplications are kind of working, and we will follow this similar step for the future steps also. So once that is done, we kind of produce the qk transpose, and that we multiplied with v. V is again 1 cross 4096 vector, right? So the output will be attention matrix, which will be the first output token, right? So the output token 1, and the shape of that would be 1 cross 4096, right? So we start with the input token, which is like a token, the first token, which can be a start of sentence token also, and then we kind of multiply with like the corresponding token 1 for the key matrix, and also we get the query k transpose as a matrix multiplication operation. Then we kind of do the multiplication with v, and we get a output token 1, which is like a 1 cross 4096 embedding size, right? Then what we do is we kind of keep the first token as it is, and we append the second token, and we also append the second token associated with the key matrix, right? And we kind of, after doing this operation, which is like 2 cross 4096 multiplied by 4096 cross 2, so which will produce like 2 cross 2 vector, and that we multiply with a v vector, which will again produce output, which will be a shape of 2 cross 4096, right? So you can already see the repetition which we are doing, right? So we are kind of generating the output token 1 again when we are producing the output token 2, right? And then similarly for the third step, we will get the third token, and we kind of do the matrix multiplication operation, which will produce 3 cross 3 qk transpose matrix, and that will be multiplied with a value vector, and we get a output token 3, right? So if I talk about the last output token, right, the output token 3, so you can see like that time also we are kind of generating the output token 1, output token 2, and output token 3, right? So these are kind of the repetitive tasks which we are doing, right? So if I just visualize the output, the attention matrix, which is like the qk transpose, so I'm just talking about this qk transpose. Here we can see like this matrix actually I'm talking about. Here we can see once we are generating the last token, the token 3, right? So we are also generating the token 1 and token 2, but this token 1 and token 2 is also generated during the second step, right? And when we are generating the token 2, that time also we are generating the token 1, which also got generated in the previous step, right? So a lot of additional steps that we are performing in this operation, and that is kind of very repetitive in nature, right? So which I have like marked it as kind of a repetitive steps which we are doing during this qk transpose process. And also if I talk about the output, right, so in the last token, if I again concentrate about the last token, which is output token 3, that time also we are kind of we are generating the output token 1 and token 2, which we have already done in the previous 2 steps, but still we are kind of generating that, right? So that is also a kind of repetitive task which we are doing. So what we are trying to do using this KV cache thing is, can we cache a few of the repetitive computations that we are doing, and we can reduce this multiplication operation and make this process simpler, and the inference would be much more faster, right? So let's try to do how we can do that using KV cache. Okay, so just carrying on with the same example. So at first, the first step is same what we have discussed previously, just that I have added the dimensions for your understanding. So we have the token 1, which is associated with Q. We have the token 1, which is associated to K transposed. Then we kind of do a matrix multiplication of 1 cross 4096 multiplied by 4096 cross 1, and we get the output as 1 cross 1, which we again multiply with a V vector, which is 1 cross 4096, and get attention matrix, which the shape is like 1 cross 4096, right? Now what we do in case of KV cache is, we kind of replace this the token which is associated with Q matrix, and that we replace with the token 2, right? So previously it was like we were appending the token 2 along with the token 1. Here we are not doing that, and we are only using the token 2 as kind of the matrix for Q, and then we are caching the values which are related to K and V, right? So you can see like both the tokens are present, token 1 and token 2 are present in case of K and V. That's why we call it as KV cache. So we are kind of preserving these two tokens, and we are kind of replacing the tokens which are related to query vector, right? And then once we do this multiplication operations, what we will do is we will get only the token 2 as output, right? So here we are not generating the output token 1 again, so we are only generating the output 2 at the second step, right? Similarly, what we do is at the third step, we kind of replace the token related to Q matrix with token 3, and we are kind of preserving the matrices, where we are kind of caching those matrices, and also we are kind of generating this QK transpose with a lesser operations, right? So previously it was kind of a 3 cross 3 after the third step, but here we are kind of generating 1 cross 3, right? So this 1 cross 3 will be multiplied with 3 cross 4096, which will result in generating only the output token as 3, right? So which will be a shape of 1 cross 4096, right? So here we can see that we are caching the matrices which are related to which are related to K and V, and we are kind of replacing the tokens for query matrices, which results in lesser computations, and which will also hope you got an understanding of what this KV cache is. And with this, in the next video we will try to understand what is a rolling buffer cache. Alright, so in this video I'm going to talk about rolling buffer cache. Now let's talk about what this rolling buffer cache is. So if you have gone through this playlist, you have seen that I have discussed about sliding window attention, then also I have talked about the KV cache. So instead, like if you have gone through these two videos, so this will be much more easier for you to understand. In case you haven't watched these two videos, I will request you to just go back and see these two videos and then come back and watch this video, right? So in case of sliding window attention, if you remember, like we have a window size of 3, and the tokens which are beyond the window size of 3, there we are applying the mask. So this is along with the causal mask which we are applying here, and we are also applying the sliding window attention, where we are masking the tokens which are beyond this window size of 3. Now what we are doing in case of KV cache is, instead of like caching everything, we will cache only the key and the value matrices, and rest of the matrix like Q matrix will be replaced by the new tokens that we are getting at each timestamp, right? So with this we are kind of avoiding the repetitive task, and also the task which we are doing in the previous step that we will not do in the current step, right? So this is the basic concept of sliding window attention and KV cache, and these two concepts we will apply in this rolling buffer cache. Now if you understood the concept of KV cache, and if just imagine that we are at the 7 token generation, right? So the query matrix will have token 7, the key matrix will have all the tokens starting from token 1 to token 7, and then we kind of multiply this q cross k transpose and we get the qk transpose matrix, which is like 1 cross 7, and then we kind of multiply with the v matrix, which is again cached using the kv cache, and there we will have like 7 cross 4096 is the shape which we are 4096 is the dimension which we are using, which is nothing but the context length of this model, and then we get the output token, right? But if you know the concept of sliding window, right? So if you are using a sliding window 3, then the tokens which are beyond the sliding window, do we at all need that in case of like storing the kv cache, right? So we actually don't need, because if we are using the kv cache, those tokens will not be used while calculating the attention metrics, right? So this is the highlighted part where we don't need this part, right? So like 7th is a current token which we are generating, so the tokens beyond 5, right? So like token 4, 3, 2, 1, those tokens we will not need to cache in case of we are applying the sliding window along with the kv cache. So what we can do is we can throw away those tokens and only cache based on the sliding window size, right? And then we will like further generate the future tokens using this concept. So this is how it works in case of particular example. Let's talk about that, right? So just imagine that we have input sequence which is attention is all you need. So this is, then what we will do is we will keep a pointer to see if the if the size of the cache is full or not. In case that is full, what we will do is we will replace the first token with the new incoming token, right? So for this example, like this was like the first window which we talked about, then the new token is coming up here, right? So that u will be replaced here and attention would be removed, and this u will be pushed to the cache, right? Now what we will do is, so this kind of spoils the ordering of the sentence, right? So if you look at this, u is all, right? So that is actually not the actual sequence in case of the original input sequence. So this is my input sequence, and if we just using a pointer, if we just remove the attention and then push the u token to the cache, so this actually is the kv cache, right? So this will kind of degrade the ordering of the sentence. Now what we can do is we can just rotate this, right? So what we will do is we will, right? So your ease will come here. So this is will be ease. Your all will come here, and the new token which is u, that will be pushed back here, right? So in that way we can like preserve the original input sequence meaning, and we can like pass the sequentially and maintain the sequence of the input sequence that we are pushing for the this thing, right? So that is what we actually call as rolling buffer cache. So we kind of roll the input tokens according to the sequence of the sentence, and in that way we kind of implement the rolling buffer cache, right? So this is actually what we are doing. So we are kind of shifting these things here, and we are bringing the u here, right? So similarly in case of the need, what we will do is at first we will put the need here, and then we will have all and u. After that what we will do is we will swap this, right? So what we will do is all u need. So in that way we will roll the cache and we will get the new cache in this manner, right? So this is the concept of rolling buffer cache. So this is just a combination of the kv cache along with the sliding window attention. In this video I want to talk about prefill and chunking. So let's first understand why we need a prefill and chunking, right? So if you remember the videos which I talked about the kv cache, so there we kind of like pass on the each of the tokens, then kind of generate the next tokens, which is kind of also we kind of cache the kv the key and the value vectors, and with that we are kind of generating the attention metrics related to this each of these tokens and then in the subsequent tokens, right? But in case of like we are using in case of like prompting, right? So prompt is always we know beforehand. We don't need to come up generate the prompt in case of like we are passing a question to a RAG. In those cases we don't need to like generate the tokens by tokens in case of the prompt, right? So as we always know the prompt beforehand, so can we pre-fill the KV cache with prompts to optimize the performance and generate the future tokens, right? So can we do that? Let's talk about that, right? So what we can do is we can like cache everything, the whole prompt into the KV cache, and then generate the answer using the what is the content of KV cache. But what happens if your prompt is a very long, like 5,000 to 8,000 tokens, which is generally the case in case of you are asking a question to a RAG, right? So in those cases, if you are trying to load a prompt which is very large in the number of tokens, so in that case your cache may not optimizely work, right? So your cache may be crash, right? So to tackle that, what we can do is we can like generate the tokens one by one, but again that will give you a not the optimal performance, right? You will not utilize the GPU that is already available. So can we strike a balance between filling the cache with one by one token at a time or loading the KV cache with the full prompt, right? So is there a way to kind of strike a balance between these two approaches and load the KV cache with the prompt, right? So the answer is chunking, right? So in case of chunking, what we will do is we will chunk the prompt with the window size. That window size is same as the sliding window attention we have used, and then we will pre-fill the KV cache with those chunks which we have created from the prompt with the help of window size, right? Example and try to understand what this prefill and chunking is. So we will take an example of this, which is kind of an input sequence or a prompt. So this prompt is attention is all you need, stood the test of time, right? So this is kind of a sentence which I am using. So I could have used the attention is all you need, but I wanted to a longer sequence to show you how the prefill and chunking works. And let's take this as one of the input sequence or the prompt, and then let's see how the prefill and chunking works. So at this point of time your KV cache is blank, right? Before this is the first time we will create the chunk, then we will kind of create the attention metrics and so forth, right? So at this point of time you can see the KV cache is blank and we are using a window size of 3, and we have chunked the input token or the input prompt in the size of in the window size of 3. So attention is all is kind of your first chunk, and then you need stood is kind of the second chunk, and the so forth after that. So what we will do is we will have this we will calculate this attention matrix. So the first window or the first chunk, which is attention is all, so that will be fed to your query and the key matrices, and with that we will kind of create the attention matrix, which is kind of a multiplication of Q multiplied by K transpose, right? And we will also apply the mask which are related to the causal masking, right? So after that, this is the first step, and now we can fill the KV cache with the with this output of this operation, right? So now let's see what this is. So first we will like fill the KV cache. So once the attention matrix is calculated, then only we will fill the KV cache, right? So here we have this content which is attention is all. So this is kind of presently available in the KV cache, and now the second chunk will come, right? So the second chunk is you need stood, right? So what we could have done is we could have like use you need stood in the query and the key matrices, right? But we will not do in case of the prefill and chunking. What we will do is we will kind of bring certain contents from the KV cache, and also we will use the current chunk, right? So the current chunk is you need stood. So if I just take the pen, so this is your kind of the current chunk, right? And this is what is present in the KV cache. So this will come here. So in the query matrix your current chunk will be used. So this is nothing but the current chunk, right? But in case of the key matrix, what we will use along with the current chunk, which is this, we will also use the content of KV cache. So this is your content from KV cache, right? So that we will use, and with these two contents, which we will only use for the K matrix, and then we will calculate the attention score, right? And you can see, like, we will also apply the sliding window attention mask. So the tokens which are beyond the sliding window, those will be marked to minus infinity, right? So now what we need, why we need to use this extra contents from the KV cache, right? So if we don't use the KV cache, we will only use this part to generate the attention matrix, right? But this token, right, right, if you just think this token, this lacks the context, right? This is actually related to all these tokens which are present in the KV cache. So to give more context to the current tokens, or which are related to the current chunk, we kind of bring the content of KV cache, then we kind of calculate the attention matrix, right? So this is actually the concept of prefill and chunking. So we will use the contents of KV cache along with the current chunk, and we will keep the contents of query matrix which is same as equals to the current chunk, and then we calculate the attention matrix, right? Now let's see what will happen in the third chunk, right? Now what we will do is we will pick up the contents of KV cache. So the previously we calculate the attention which is related to need stood, right? So that will be available in the KV cache, and now the new content or the new current chunk which we will get is the test of, right? So to give the more context, we will bring in the contents from KV cache, and we will also use the current chunk from the input sequence, and that we will use in case of the K matrices. And the query matrix, as I mentioned previously also, so that will be same as only the current chunk. So this will be used here, and this is actually coming from the KV cache, and this is actually again the current context, right, or the current chunk. So in this way we will kind of prefill the contents of the KV cache, and also we will use the chunking concept to kind of utilize the prompts which we already know the content of, right? So in that case we don't need to generate the token by token each of the prompt content, and then kind of ask the LLM to get the answer which is related to the prompt, right? So I hope you got an understanding of what this prefill and chunking is, how we can use it to kind of optimize the KV cache in case of the prompt, right? And it also kind of strikes a balance between loading the prompt tokens one by one, and also like loading the full prompt to the KV cache and then do the inference, right? So this chunking, prefill and chunking, kind of strikes a balance between those two approaches, and it gives you the more optimal performance. Alright, so in this video I want to talk about the mixture of expert, which is actually the mixtural model. So let's talk about this. So this is, and where we can see like the input goes through an embedding layer, then the embedding gets generated, which then gets normalized with RMS norm, and then we add the rotary positional encodings to the query and key matrices, and the V is kept as it is. Then we kind of do the certain tasks which are related to the attention mechanism, like sliding window attention, grouped query attention, then there is a rolling buffer KV cache. So all this I have discussed in this playlist, and the only thing that is being left is the mixture of experts part, right? So here we can see that this is our mixture of expert, which is nothing but a feed forward network. So there are actually 8 into 7 billion models are there. So there are 7 billion models which are nothing but a feed forward network layer which is present here. And before going to the feed forward network, we have a gating mechanism here. So don't worry about each of these terms. This is just that the new things which we will discuss in this video, I am adding it to the diagram, and we will discuss what this gating mechanism is and what is this MOE. And also here we kind of, once we get the output, we take a weighted sum or average, This is actually a weighted sum or average, and then we kind of produce the output, which again goes through RMS layer, then it goes through a linear layer, which kind of produces the logits for each of the tokens in the vocabulary. Then we take the softmax to select the particular token which is related to the input, right? So this is kind of a high level architecture of the whole mixture of experts, and I have kind of discussed each of these components in detail in this playlist. And if you want to understand the mixture of experts, so this is the video where you should look. Now let's talk about what this mixture of expert is, right? So we have our input. This input goes through a gating layer. So this in between we like kind of do those extra stuff which are related to attention mechanism, like sliding window attention, the grouped query attention, then there is a KB cache with rolling buffer. So all this we do, then we pass it through a gating layer. So this gate layer actually kind of selects the 2 out of this 8 experts, right? So in fact this gating layer is kind of a feed forward network which kind of generates the logit, and based on those logit values it selects the most probable 2 experts for each token, right? So that is quite important. For each token the 2 experts are getting selected. So at first, like based on the logit score, the expert 3 is selected and also expert 7 is selected. So this is just an illustrative purpose. I am showing that 2 experts are selected out of the 8 experts that are present here, and each of these experts are nothing but a feed forward network that is part of the feed forward network in that whole Mistral architecture, right? So once that is done, what we do is, using those logit score which are being produced by the gating mechanism here, we kind of use a softmax to get the weights. So once we get the weights, what we do is we calculate the weighted sum or average using those weights, and we produce the outputs. So if I just try to explain with like what this logit and weights mechanisms are. So for each of this expert, this gate kind of produces a logit value. So just for illustrative purpose, I'm taking the random values, like this is 1.3, this is like 1.01, so this is like 1.99, and similarly we have like other random values. So I'm just taking, and also for this we are saying that this is 1.90, right? So we can see like the highest values are this 1.90 and 1.99. So based on that it will select this expert 3 and expert 7, and using this logits then we will apply a softmax here to produce the weights. So these weights will be normalized values, and that normalized values will be in the range of 0 to 1. So for an example, like this is kind of the highest weight, so that is being produced here. So say for an example, say like this is like 0.60 and this is like 0.40. This is again randomly I'm using this weights. Actually this 2 values will be used and this 2 values will be softmax to get this weights, right? So once we produce this weights, so using those weights for every token we kind of create a weighted sum or average, and then we produce the output. So this is actually the high level overview of what the mixture of experts look and how the data flows through this mixtural architecture of this mixture of experts, right? Now the question comes, why we are saying this as sparse mixture of experts, right? So as you can see here we have like 8 experts, but we are only selecting 2 experts out of these 8 experts. So it's not that all the 8 experts are being used to calculate the weighted sum or average then produce the output. Only 2 of them is selected. That's why we are saying that this is a sparse mixture of experts. So if we are selecting all the experts, then we will not say that this is a sparse mixture of experts. So that's why we kind of use this term and we call it as sparse mixture of experts. Right, now let's talk about few of the details of this architecture. So first of all, like each experts, which is a 7 billion model, is trained on a subset of data, so that each expert is specialized on a certain task, right? Then this gating layer, which I have shown in the last slide, right? So this gating layer is a linear layer which was trained along with the experts and also with the rest of the models. So it's not that this gating layer was trained in a separate process. So it is part of the whole training process, and it is being trained with along with the experts and the rest of the model, right? And each input tokens embeddings, so once the input comes, the gating layer produces kind of 8 logits for each individual experts, which is being used to select 2 experts with the highest logit values, right? So which I also explained in the last slide, that the gating layer will produce the 8 logit values which is corresponding to each of the experts, and which two the highest 2 logit values will be selected, and those 2 experts will be selected. Then the input will go pass through those experts, and then we will use a softmax to kind of normalize those 2 logit values only to get a weighted weights out of those logits using a softmax, and then we kind of do a weighted sum or average, and we get the we produce the outputs using that, right? So then this sparse mixture of experts allow us to increase the parameters of the model, right? So we can see like here 8 experts are present, with each of them are 7 billion models, right? So we kind of increase the model parameters, and it has been seen that in case of large language model, the more parameters you have, and the better the performance is, right? So that we have seen in case of the progression of like GPT-1, GPT-2 and GPT-3.5 and the GPT-4, right? So every time the model parameters got increased by huge margins, and the model performance also got a boost with that. So that they have also tried to use that in the mixture of experts or the mixtural model, but the computation or inference time is kind of remained same, right? So because we are only using 2 experts out of those 8 experts, and then we are doing the intermediate steps or the matrix multiplications, so that the inference time is kind of same across this whole increased experts and the model parameters.
Right. So let's first talk about the different phases of LLM training, right? So the first phase is the pre-training phase, which we also call as language modeling, right? So in this phase, we mainly train our LLM on a large scale of data set. That is a large data set we will use to train a model, and this large data set is on a scale of like over 1 trillion tokens. So these tokens are nothing but, if we are thinking about a sentence, right? So each of the words can be one of the token. Now each of the words can be also split into multiple tokens, so that is a different concept, but just imagine that we are kind of training this model over 1 trillion tokens, and those tokens are mainly scrapped over the internet, right? So with this concept, what we will do is we will mainly optimize this model for text completion or the next token prediction task, right? So this model is not, now at this point, this model is not ready for conversational task, right? So if you go and talk to this model will not give you the results which you desire for, right? So that is one of the drawback of this model. But what we get is we can treat this model as kind of a completion machine, which is like excels at the task of next word prediction or the next token predictions. So some of the examples are like GPT series of model which comes from OpenAI, then there is Llama from Meta, and also the Stable LM from the Stability AI, right? So at this phase, you can think this model as kind of a untamed dinosaur, right? Which is kind of a huge model which is trained on very large amount of tokens, which generally spans over like 1 trillion tokens. And this model is kind of a very huge gigantic dinosaur which you can think of, and this model is not optimized for conversational purpose, right? So now the next phase is, or the second phase is supervised fine tuning, which we also call as SFT phase, supervised fine tuning phase, and we also call it as instruction fine tuning, right? So in this phase, what we generally do is we use high quality data, which is mainly focused for conversational AI purpose, right? So we train our train our language model with a high quality data set, which will be better suited for the conversational AI, right? So, and this data set is comes in a format which is like a prompt response format. So we have like the prompt or the questions, and also the corresponding response. So this we generally call as demonstration data, right? So with this, the main goal for this phase of this LLM training or this SFT phase is to optimize the pre-trained model to generate responses that users are looking for, right? So you will train with this prompt and response pairs, which we also call as demonstration data, and then we assume that the model will excel at the conversational task. So if a user asks a question to this model, then the model will understand that context of the question, and it will give a better result while comparing with the first pre-training phase, right? So the goal is to optimize the pre-trained model to generate responses that users are looking for, right? So OpenAI kind of calls this SFT as behavior cloning. So what this behavior cloning is, you demonstrate how the model should behave, and the model will clone that behavior, right? So we are kind of demonstrating that behavior using this prompt and response pair, and we expect the model to just clone that behavior so that it will excel in the conversational task, right? So some of the examples are like Dolly v2 or the Falcon Instruct, and the demonstration data that we are using here, that scales over like 10,000 to 100,000 prompt response pairs, right? So the volume is kind of decreasing. Like we started with like a data set which spans across trillion token, and now we are kind of reducing that data set, and we are kind of passing a high quality data set to the model which scales like 10,000 to 100,000 prompt response pairs, and we are expecting that the model will excel at the conversational AI task, right? So now we can say that we started with a like untamed dinosaur. Now we are kind of get a grown up child which can understand the user questions or the questions coming from different sources, and it will be able to answer those questions, right? So those answer may not be perfect, so that is kind of the drawback of this supervised fine tuning process. So let's talk about so far like what we have gone through using this diagram, right? So this is from one of the famous blog from Chip. So what we start with a low quality data, and those are kind of scrapped from the internet. Then we kind of pass those data through a language model, and we kind of get a pre-trained LLM, right? So the scale is like greater than 1 trillion tokens, and the examples are like Falcon, GPT series of models, then Bloom, Stable LM. All these models are kind of pre-trained models. Then using that pre-trained model, what we will do is we will pass the demonstration data, which is kind of a prompt response pairs, and we fine-tune our model which will excel at the conversational task, right? So for pre-trained model, that is excel at completion task or the next word or next token prediction. But using this SFT training process, we will get a model which can also excel at like conversational AI stuff, right? And this data, which is like a high quality data that has that ranges from 10k to 100k, right? Prompt response pair. But after all this, you may not get the optimal results, right? So even after fine tuning process, the model can still perform poorly on several alignment criteria, right? So what are these alignment criteria are? So let's discuss about that. So helpfulness is one of the criteria. So you are kind of putting some questions and you are asking some sort of help, but the model may not give you your desired output, which is may not be helpful to your question or to your context which you are passing as a prompt, right? Then there are several other alignment criterias like harmfulness. So model may be giving certain responses which may be in terms of toxicity also it is kind of performing bad, and also it is kind of spitting out some harmful behaviors as a response. Then there is honesty, so model may not give you the response in an honest fashion. And the last but not the least, it can also hallucinate, right? It can make up like its own answers, and then it will give you that response as a prompt, right? So with all this, these are some of the general alignment criteria, which is the SFT model still suffers. And using like bringing the human in the loop with the help of reinforcement learning with human feedback, we expect that model will kind of perform well on this type of task or this type of alignment criteria, right? So as we kind of started with reinforcement learning with human feedback, now first I wanted to take you through some of the basics of reinforcement learning. So this is kind of a refresher of reinforcement learning concepts. So first, reinforcement learning is kind of a subset of ML. So generally this reinforcement learning is a subset of ML, which is different from the conventional supervised and unsupervised machine learning, right? So few of the characteristics of the reinforcement learning, like humans, the reinforcement learning algorithm also learns by interacting with the environment, right? These interactions are often sequential in nature, and the learning which happens, that is active learning rather than the passive learning. And the model can also learn without seeing the optimal examples. So with its own intelligence, if you don't provide also the optimal examples, it can still learn that without seeing optimal examples, right? And this algorithm is generally goal oriented algorithms, which aims to maximize the long term rewards, right? So the main aim of this algorithm is to find the long term rewards, right? Now a typical reinforcement learning example, right? So after exam childhood days, right? So I hope you remember that. So when we used to get like good marks in the exam, we used to get candy from our parents or from teacher. We used to get some positive reward, right? But if we are performing bad, then a stick or some other treatments for the bad result, right? So this is a typical set of reinforcement learning problem. I hope you got an understanding of how the basic of reinforcement learning works. Now let's talk about how reinforcement learning is different in while compared with the machine learning, right? So first of all, the aim is to choose the optimal task in case of reinforcement learning, or choose the optimal action. What this action and what the terminologies which I am using, that I will talk about in very much in detail in the next few minutes. But for the aim of a machine learning task is to predict, classify, or grouping is nothing but the clustering, right? So then there is uncertainty over the environment, right? So but in case of machine learning, the data set which we are passing to the model, which is X, that is fully known. So environment is fully known for the machine learning. But in case of reinforcement learning, your X is not fully known, so you do not know the environment fully. So you learn by interacting with the environment. Then it learns by exploring the environment in case of reinforcement learning, and for machine learning it learns by finding the patterns that are available in the data. The training process outcome for reinforcement learning is the optimal policy, and for machine learning the training process outcome is the best model, right? Then there are dependency in the previous action that the reinforcement learning model has taken. But in case of machine learning, each observation is kind of independent in nature, right? Okay, now let's talk about the few of the terminologies. First of all, like the agent. So agent is kind of the algorithm which we are trying to build. Then the agent takes certain actions, the set of possible actions the agent can take, that we call as action. And agent interacts with the environment. So environment receives an action and produces a new observation and reward. So that reward is kind of an indication how the agent is doing at a particular timestamp, right? So this reward is generally a scalar feedback. That you should remember, that the reward is kind of a scalar feedback, because this concept we will use when we talk about the RLHF, right? So it's not only the environment kind of emits the reward, it also emits a new state So based on the action, the agent will move to a different state, and that state is kind of a representation of the agent in the environment, right? So using the state representation, the RL algorithm picks the next best action, right? Talk about a few two different concepts which is very much required for understanding the RLHF process. So first of all is like what is expected value or the reward, right? So the weighted sum of each possible outcome is kind of a reward. So if you are in a stochastic environment, right, so your action, like if there are two paths, right, and your action kind of depends on has a separate probabilities, right? So being on a state S, there is a 60% chance that you go to a different next state, and also you kind of have a another 40% probability of going to a different state where the reward is kind of 0, which is associated with 0.4 probability, and also we have a reward which is associated, reward equals to 1, which is associated with 0.6. Now the cumulative reward which being at state S the agent might get is kind of the, you have to multiply each of the probability with the reward value, then sum, and then you will get the total reward or the expected value, right? So for this example, if you multiply zero point 0.6 with 1, you will get 0.6, and then you multiply with 0.4 with 0, you will get 0. So the expected value or the reward for being state is equals to 0.6, right? Then we have this concept of value function, which tells you how good is any given state for an agent, right? So for a deterministic world where there is no randomness in the environment, so the action you are desired to take, you will always able to take that action. That is kind of a deterministic world, right? So the value of a state is just the sum of all the future rewards, right? So if I take this example, like the agent is at the first step, then it will like traverse through different paths of the this maze, and it will finally end in a final state, right? So being at state 1, which is S1, the value function is kind of the sum of all the future rewards, right? So if you like visualize this process as the future rewards are like R2, R3, R4 plus till it will go to the last reward, which is Rn, right? So that is kind of which tells you the value function for being at state S1, right? So if you just simplify this equation, right, so now we can write down vs2 is nothing but r3, which starts from r3 because we will only sum the future rewards, right? So from r3 it will go till rn, right? So that is a representation of vs2. Now we can plug this vs2 in the first equation, and we can get the vs1 is nothing but r2 plus vs2, right? So now there are certain uncertainties in the environment, right? So your future rewards is not very easy to predict, right? So we kind of implement we can bring in a multiplying factor, which is a discounting factor, and as there are uncertainties in the future reward, so because it's always harder to predict the future rather than the next few rewards which are very soon to happen, right? So we can bring in this discount factor and we can represent the value function like this, right? And for stochastic behavior, which we use as Bellman equation, so here we kind of straight away we cannot sum all the future rewards, so we need to take the expected value of the future rewards, right? So which I already talked about at the starting of this slide, right? So this vs is nothing but the expectation of r plus discount factor multiplied by vs dash, right? So this s dash is nothing but the next state, and r is the reward from going from s to s dash, right? So you are starting from a state which is s, and the next state is s dash, right? So that is kind of the expected value for stochastic behavior, right? Of this reinforcement learning refresher part, so we will talk about what is policies, right? So policy is kind of a function that maps a given state to action, right? So that action can be deterministic in nature, so you always get you always get to perform the action you desired for. But if there are certain uncertainties in the environment, so then we kind of bring in the probability of actions, right? So if you just take an example of a agent is kind of moving in a maze, right? So if that maze is not slippery, then that is kind of a deterministic action. So if the agent is trying to go in a forward direction, it will always end up in the forward direction path, right? But if that maze is kind of a slippery and there is no certainty that if the agent wants to move forward, it will always end up in the forward direction. It can move into a different direction due to the stochastic nature of the environment, right? So if an agent follows a policy pi at a time t, then pi of a given s means that at time t under the policy pi, which is the agent is kind of following a certain policy, right? So the probability of taking an action is probability of taking action a in state s is pi a given s, right? So this is how you can denote a policy. So policy is nothing but which maps action on a given state, right? So for deterministic policy is a equals to pi s, but in case of stochastic environment, so you will come up with a stochastic policy which is nothing but pi of a given s, right? So which is nothing but probability of taking action equals to a being in the state equals to s. This is what I was trying to explain. Like if you are in a state b and if there are a stochasticity in the environment, so if you want to move to a particular direction, it may not happen that you will always end up in that desired location, right? So there are probabilities associated like going left, right, and also there is a probability associated being in the same state, right? So this is kind of a representation of the stochastic policy, and where the probabilities are associated for each of the action. And for stochastic policy, you need to use the probability as one of the parameters, right? So all of this reinforcement learning thing which we are talking about, the main aim or objective is to find the optimal policy, right? So what this optimal policy is, a policy that is better than or at least same as all other policies is called optimal policy, right? So if we have two policies, right, pi 1 and pi 2, now we have two states, right, s1 and s2, and we also know the what are the value functions for each of these states for different policies, like for the policy 1 and policy 2. So here you can see like the policy 1 is kind of better performing while compared to the policy 2. So in the S1 state, both the policies is kind of giving you the same value function, but for S2, your policy 1 is kind of giving you better rewards or the better value function, right? So with this criteria, we can say that pi 1 is kind of greater than or equals to of pi 2, right? So if you want to pick a policy for this particular environment, more or less we will always pick the pi 1, right? So now let's talk about what this reinforcement learning human feedback is in a detailed manner, right? So first of all, this is like the whole phase of LLM training, right? So we at the first phase, using a low quality data, we get a pre-trained LLM. Then using a high quality data, we get what we also call as demonstration data, we got the SFT model. And then the RLHF part comes in, where using human feedback, at first we will train a reward model, and then using that reward model, we will implement a reinforcement learning algorithm to make the model outputs or the LLM outputs which are more aligned to human feedback, right? Or more aligned to the several alignment criteria which we talked about, right? Like helpfulness, toxicity, and hallucinations. Those we will try to reduce using this reinforcement learning from human feedback architecture, right? And now let's zoom into this RLHF part, right? And let's talk about that in detail. So at first, as I was mentioning, we have the reward model. So if you just look at this first phase of the RLHF, using the pre-trained model, we get the SFT model, and in the using the SFT model, we will try to build a reward model. Model generally takes as input the output or behavior of an AI agent. So in our case, this output is will come from the SFT model or the supervised fine tuning model that it will take as input, and it will produce a scalar reward, which is kind of a signal which will quantify how well the output is kind of aligned with the human preferences, right? So with that, let's try to understand what this reward model is. So this reward model basically is a classification or regression model which is trained to give a scalar score on the responses based on the human feedback, right? So we will deploy certain labelers, the human, so that those human will generally get the prompt and the response from the SFT model, and then it will kind of try to score those outputs, right? So what we can do is we can straight away ask the levelers to give a score between 0 to 10 based on a certain alignment criteria, but that score may not be consistent across different levelers, right? So each of the human being has several thought process, so they may not give a consistent score. So what we generally do is, we, instead of giving the scores, we ask the levelers to compare the two responses and decide which one is better, right? So for an example, if we have a prompt like how can I get my dog high, right? So we have two responses, right, from the SFT model, which is, one of them is like, I am not sure what you mean by that, and then they kind of the answer which the LLM is kind of hallucinating and giving some garbage output, right? So we both of this response, we kind of ask the labelers to mark it as a winning response or a losing response, right? And this data set which we kind of collects in the scale of like 1000k to 1 million data set, that we also call as comparison data. And then the main task is to convert this winning and losing response to a proper scalar reward value, right? So using this data, like the prompt and the winning response and losing response, we kind of pass this data to a model that we generally call as reward model, and that reward model, using a proper loss function, will give you a scalar feedback value. So first of all, we have the prompt. That prompt, we kind of pass it through the instruction fine-tune model or the SFT model, and we get a kind of model generated response from this, and that we kind of pass it to the human labelers, right? So those human labelers will kind of create the comparison data with the help of like marking each of the responses as a winning response or a losing response. Then with that, we will build a data set, which is kind of a data set that will be used to train the reward model, right? So with that comparison data set, we will try to train the reward model, and the reward model will kind of give us the scalar feedback of each of this prompt and response pairs, right? So I hope you got an understanding that we kind of get the output of from the SFT model, and then we ask the human feedback to incorporate the human feedback to mark each of the responses as winning response or losing response, and then we kind of build a data set which is kind of a comparison data set. Using that data set, we will train a reward model, which can be a classification model or a regression model, and that model will give you a scalar reward value as an output, right? So that is the main idea of reward model. Now using that reward model, we will try to optimize our LLM for the RLHF process, right? So let's visualize this whole process, right? So we have the prompts, then we have the instruction fine-tune model, and we also create a copy of that which we call as instruction tune model frozen. So here the weight updates will not happen, so the weight update will happen in the in this like unfrozen model of the instruction fine-tune model, right? So once we have that, we kind of pass the prompt through the model, and we kind of get the response from this instruction fine-tuned LLM version, right? And we can also get the probabilities of the tokens, and using those probabilities we get a probability set up from the frozen model and also from the unfrozen model. Then we use a concept of KL divergence. Now why we use the KL divergence, that I will talk very much in detail in next few minutes, but we generally don't use solely the reward model as kind of an indication how the model is performing. So we kind of incorporate this reward model output and also the KL divergence output, and then we kind of give that as a reward model to the RL model, right? So this RL model we generally use as proximal policy optimization algorithm, which I will also talk about in detail. So using that algorithm, we will kind of do the weight updates to the trainable instruction fine-tuned model, right? We will do the weight updates, and this process we will go through multiple times to get the weights in a more optimized fashion for our alignment criteria, right? Now let's talk about why PPO and why we talked about the KL divergence, right? So this PPO, or the proximal policy optimization, is kind of a policy optimization methodology where we have a constant optimization which we will try to do. So the optimization function or the objective function looks like this. So this is kind of a policy gradient optimization function where we have the log probability of taking an action at a given state, which is for that particular policy, which is the first part, and then we multiply with the advantage function. So this advantage function you can think as a value function. So if the advantage function is greater than 0, then that particular action is better than the other action that are possible in that particular state, right? So this is kind of objective function. So but this objective function has certain issues, right? That we will talk about. But the main objective is to, by taking a gradient ascent step on this function, we would push our agent to take actions which will result in a higher rewards, and which will also avoid harmful actions, right? So now let's talk about what are the problems associated with this simple objective functions, right? So if you just visualize a policy which we are trying to do a policy updates, right? So if you are doing a smaller policy updates, we know that the training algorithm will likely to converge in more or less some time, right? Which can give you the optimal solution. But if your policy updates are very big and the policies are taking very big steps, then it can result from falling off the cliff, right? And once you fall off the cliff, it will be very hard to recover, right? So we kind of try to strike a balance between small updates and larger updates. That's why we kind of introduce the concept of proximal policy optimization, where that architecture kind of improves agents training stability by avoiding too large policy updates, right? And here we kind of use uh, a clipped surrogate objective function. So this, if you can see this first part, which is like L clip theta, where we have like expectation, then we have this RT theta, which is nothing but a ratio function, and then we kind of clip that RT theta within a certain range, and then we multiply with a AT hat, right? And we kind of take the minimal of these two things, right? So the minimal of RT theta multiplied by AT hat, and also this cliff function multiplied by the advantage function. So what this R theta is, so this R theta is nothing but a KL divergence, right? So it is the probability of taking an action at a state S in the current policy divided by the previous one, right? So you can see that it is kind of a ratio of the current policy, and which compares the value with the previous policy, right? If this value is greater than 1, right, and if it is a very large value, that means your current policy is kind of diverging from the previous policy, right? So that we generally try to limit using this cliff function. So we will limit the RT theta value within certain range, and which will kind of restrict the algorithm to take smaller decent steps, which will kind of follow the previous step, and also your policy will not fall off the cliff, right? So with this concept, we will try to implement the PPO, and so in case of LLM configuration, right? So what we do is we kind of implement the similar concept using in case of LLM, right? So we have a reward model, and we have two models, which is like LLM SFT, which is the supervised fine-tuning model, which is kind of the frozen model, and which kind of tells you the what our previous policy was, right? And this LLM phi RL is the model being trained with reinforcement learning, which is parameterized by phi, right? And our goal is to find this phi to maximize the score according to the reward model, right? And we have like prompt and response pair, which we pass as a input to our RLHF model, right? So now what we can do is we can combine these two, like a reinforcement, like the reward model output, and also we kind of bring in the scale divergence function, which will limit the current updates to the LLM to deviate from the SFT model, right? So if your updates are very big, so it might happen that you are diverging from the current state of the SFT model, which excels at like basic conversational task or token generations. It may happen that you are kind of forgetting those tasks, right? To limit that, we kind of bring in this ratio function with, and we will, using the cliff function, we will limit those huge policy updates, right? So that is the basic concept of proximal policy optimization, which works well in case of the reinforcement learning human feedback, and which will do small weight updates, and the policy which it will come up with, that will kind of that will not deviate from the actual policy of the SFT model, right? So I hope you got an understanding of this reinforcement learning feedback. If you're not understanding any part of this video, please let me know in the comment. I will try to explain, right? So with this, I will end this video. I hope you like this one. If you haven't subscribed this channel, please subscribe and share this content with your friends. Thank you. See you in the next video.